trenches, looking for a way to escape. You always cut me down like a dreamer's with the grapes. But never mind how I tried to leave you behind. I kept falling in your net. Oh, I've been so blind. But I know for sure the day will come when you first realize what have you done, and you finally get you that rebate and revenge is served on a cold plate, and you hear the roar of the shutdown when the world will stop without a sound. And the moment you will cry for help, and we only think about ourselves. Oh yeah. But I know for sure the day will come when you first realize what you have done, and you finally get your debt repaid and revenge is served on a cold plate. Oh yeah, on a cold plate, on a cold plate, on a cold plate.
1, 2, check 1, 2. Okay. Hey, good morning, everybody. Welcome to day 2. Just a couple of quick announcements. So first of all, we've opened up another set of restrooms through the door here, down the hall to the right. So hopefully that makes things a little easier. We don't have quite the backlog. Second thing you'll notice is we introduced a couple more tables and some chairs. It's a fine balance between like being comfortable and being able to move about the cabin freely, right? So hopefully this works. If it's problematic, let us know. We'll adjust again. Third thing, let's see. Oh, town hall. This afternoon in the latter half of the lunch break, we'll have a town hall. We've got a list of topics to cover, but if there are things that you'd like us to be aware of as we move forward into planning HPG 2025, now's your time to give us that feedback. So for better or worse, you're stuck with me again for another year, but I'm going to take that feedback to the committee, to the steering committee, and try to roll that in as we begin preparations for HPG 2025. Okay, I think with that, we're ready to begin. Anton is our session chair, and so I'm going to hand it over to him.
Right. Good morning, everyone. It's great to see you guys this morning, the entire community. I'm going to be a session chair. It's going to be about it's going to be the session about real-time GI methods, right? Oh, sorry, not the real-time GI. The AI and denoising, of course, right? Yeah, we're going to have the first paper called Frustum Volume Caching for Accelerated Nerf Rendering. And Michael Steiner is going to present it.
Right. Thank you for the nice introduction. Good morning, everyone. I'm proud to present our paper, Frustum Volume Caching for Accelerated Nerf Rendering. First, let's give a quick introduction to Nerfs. You heard of them yesterday already, but in general, they are used to solve the inverse rendering problem, which means to learn a 3D scene representation from a set of 2D posed images. And this can be used to render them views from before not seen viewpoints, so novel view synthesis. The original Nerf paper from 2020 used differentiable volume rendering, ray marching, and evaluating a network for each sample with input a 3D sample position and view direction, and the output being outgoing radiance, so color and density. And accumulating this up per ray and comparing it to the ground truth image allows you to learn this representation. The underlying network they used was a large MLP, and this led to very large training times and far below real-time frame rates. A quick background of so this introduced many follow-up works. Most important for us will be MIP-Nerf 360, which is an anti-aliased Nerf method. So instead of evaluating infinitesimally small samples, they evaluate Gaussian blobs. They also performed scene contraction in order to handle unbounded scenes, warping them into a bounded domain, and introduced a distortion loss, which encourages the Nerf to form proper surfaces and consolidate density along the rays. Another important follow-up work was Instant NGP from 2022 by Miller et al., who introduced a multi-resolution hash encoding, which proved to be much more efficient in encoding 3D positions than the previously employed frequency encoding with large MLPs and allowed to use much, much smaller MLPs, which led to much faster training times and rendering times as well. What they also employed was binary occupancy grids, which are commonly used for empty space keeping and which are also optimized during training. A quick background, the key takeaway is that previously potentially all Nerf methods employ networks that are split into two parts. The first base network is pretty expensive usually and extracts a view-independent latent code. And the much smaller head network then gets also fed the view direction and outputs view-dependent color. So this acts as a first motivation for our method, as we want to cache these view-independent outputs to reuse them across consecutive frames and re-evaluate only view-dependent effects. Some background and related work. Previous methods tried to accelerate Nerfs by either baking them into a more render-friendly format, so training a high-quality Nerf model, and then, for example, Snark bakes it into a sparse voxel grid with neural features which can then be more efficiently queried than, for example, a large MLP. Other methods like mobile Nerf extract a mesh from a trained Nerf model, which can then be efficiently rasterized or ray traced, like we heard yesterday. This usually has the problem that it struggles with thin structures and semi-transparent surfaces. More closely related to our method, FastNerf attempted to accelerate it by splitting the Nerf into two completely separate networks and caching only view-independent codes in world space. This was only done for the original Nerf network and only for very small bounded scenes. Some other related work in the field of temporal coherence methods, more specifically volumetric ones. Image-based techniques rendered layered images, which could then be efficiently rendered using image-based rendering techniques. 3D irradiance probes were used to cache 3D irradiance in world space. More recent methods like neural radiance caching use coordinate-based MLPs to use temporal coherence also in world space. And more closely to our method, view-aligned caches employed frustum voxel or Voxel grids, for example, Vronsky and Hilaire, to cache irradiance of participating media like fog. So to come back around to our task of caching Nerfs, the general idea of our model is to cache the view-independent output of the base network in a view-aligned Voxel grid. This cache can then be sampled from nearby viewpoints to re-evaluate on a view-dependent color through the considerably smaller head network. This comes with a couple of important challenges to keep in mind when designing our method. Firstly, we'll have to be able to detect cache hits and cache misses on a per sample basis, and then also to blend these cache misses and hits along rays. Another challenge is to keep cache size reasonably small. This can be achieved by reducing the size of latent codes and using sparse data structures. Also, we require fast cache initialization so that our method can also be used for real-time applications. And critically, of course, fast cache lookups and color re-evaluation. So otherwise, our method would not make sense. And of course, we have to be able to properly interpolate samples from cache without introducing any aliasing artifacts. So let's get straight into how do we interpolate these Nerf samples. Our cache consists of 3 separate 3D voxel grids storing latent codes, density, and binary occupancy information. In general, we initialize all unoccupied cells to 0, and when sampling density from this cache, we first transform any 3D sample point into voxel space and trilinearly interpolate from our density voxel grid. This leads to no problems, as these unoccupied cells are just treated as having a density of 0. For latent codes, we have to account for this potential 0 shift by normalizing using the occupancy information. The problem in general is that the latent codes are the output of a highly nonlinear function, so a neural network, and interpolating them linearly might not give meaningful results, even for spatially close 3D samples. And to see what would happen if you naively interpolate them is here, where you see these streaking artifacts and white dots. So to induce spatial linearity during training, we shift training race by a random stepping offset in Z direction and interpolate each actual sample from 2 shifted samples. If one of those samples is outside the occupancy grid, its interpolation value is set to 0. And this behavior effectively simulates the same interpolation scheme later employed during cache retrievals. One unnecessary property of latent codes is that they are completely view independent, meaning they can be re-evaluated from a whole 360-degree viewing angle. For our temporal coherence method, however, we will only ever encounter small view changes. We therefore choose to limit latent codes to only be valid inside a cone up to a certain angle, here 22.5 degrees, so encoding a 45-degree cone overall. This has the advantage that latent codes now can be smaller, as they have to be less informative, and head networks can also be smaller due to the same reason. So, in more detail, our cone encoding produces latent codes which were generated from a view direction VC, but can be re-evaluated from a similar view direction VT lying inside the same cone of some maximum angle, theta max here. This encoding can be learned during training by carefully choosing a number of view directions, 4 in this case, and providing the difference in viewing angle to the head network and averaging the final loss of all samples. And this way, we effectively shift some computational load from the head network to the newly introduced neck network. Finally, we propose a full model which is especially suited to our caching and reprojection approach. It is based on instant NGP, but the base output is directly fed into the neck network of our cone encoding. Density is still entirely view independent, as this is essential to obtain view consistency. This now introduces latent codes which are somewhat view dependent and are only valid inside a cone around VC. Now that we are able to properly perform lookups from our Voxel grid, let's have a closer look at the employed data structures. As we already said, to reduce cache size, we want to have sparsity in our data structure. Therefore, we use sparse Voxel grid with fixed-sized bricks, for example, of size 8 by 8 by 8. And they are essentially split into 2 different data structures, one storing brick information, so occupancy, and indices, which point into the data array where the actual per sample data, so occupancy, density, and latent codes lie. Importantly, neighbors in B are not necessarily neighboring in D. They're needing some form of interpolating across brick borders. During initialization, we choose to perform brickwise initialization to fully utilize the reserved memory, and optionally we pad bricks to also store neighboring information, simplifying the trilinear interpolation so we don't have to care about brick borders. For reprojection and sampling, we perform normal ray marching and per sample check first the global occupancy grid. If it's not set, we always reject samples. A cache miss happens only if a sample is also outside a known range, which we built during cache initialization and which is valid between the cache camera's near plane and the termination depth of its individual rays. Cache hits only happen if our sample is inside this known range, if both brick and data arrays are set, and if the sample we trilinearly interpolate has high enough density. And all these checks enable us to have as few as possible false cache hits, and thereby reducing the number of unnecessary evaluations of the head network. Some quick implementation details. Our network is trained in a training framework based on PyTorch and based on the Nerf framework. Our real-time viewer and offline renderer is implemented in C++ CUDA and uses tiny CUDA in N for hash grid encoding and MLP evaluation. Importantly, although tiny CUDA in N is quite fast, all the additional encodings of our head network require us to use a custom fused GPU kernel that performs all these operations in a single kernel. And to get to our results and evaluation, we evaluate on the MIP-Nerf 360 dataset, which contains challenging indoor and outdoor scenes. And they capture 360-degree viewing angles with some central object of unbounded scenes. The models we compare against are a larger base variant of instant NGP without any further changes, a adapted version of instant NGP which employs scene contraction, distortion loss, and also has interpolation training, which we can also use for caching and reprojection. Our method, which also uses the cone encoding with a maximum cone angle of 25 degrees, and which also uses smaller latent codes and head networks. And to show scalability of our approach, we also use a model, an instant NGP model, with an even larger hash grid. Here we show model quality for base instant NGP model and ours, and we see that scene contraction and distortion loss lead to a significantly higher PSNR score, and also to drastically reduced sample counts, which translates directly into better performance. Compared to other novel view synthesis models, we simply show that we can achieve competitive results in both indoor and outdoor scenes. So in order to evaluate performance and quality of our cache renderings, we render the cache from the dataset test set viewpoints and only move the cache initialization viewpoint around its vicinity. We do this for rotational viewpoint changes, for different degrees of rotational change. Here you can also see the corresponding cache hit and cache miss masks. And we also perform the same evaluation for translational movement along the view ray. So in terms of performance, we can quickly see that our approach is much faster than instant NGP due to the much lower sample count, and that our view encoding introduces no additional overhead. Looking at cache performance, we achieve large speedups when rendering from our cache, but we can also see that as the cache hit rate degrades for larger viewpoint changes, also our speedups decrease with it. Instant NGP, on the other hand, the base model is unsuited for caching and achieves almost no speedup as the head network is simply too expensive to evaluate. Additionally, cache size is smaller for our base model as we use fewer latent codes, and using the same latent code size with instant NGP also doesn't lead to significant improvements in cache rendering performance. In terms of quality, our modifications enable high quality rendering from cache. As we can see, the instant NGP variant does as well, but here, of course, we saw that we couldn't get any performance benefits. We also see that we can faithfully render from cache when we employ even smaller latent codes. And here we see that our approach fails considerable when we do not induce spatial linearity during training. So here for rotational view changes, PSNR degrades from 30 to 24 PSNR. If we train our view encoding for smaller viewing angles, it fails to reconstruct the cache for large rotational view changes, as seen here. We also evaluated a video sequence to showcase the capabilities of our model for a 300 frame video path for predefined cameras for several scenes. And to show scalability, we used the huge variant of our model. We also employed super sampled volumetric motion blur and depth of field, which further fits our model as we can sample the same cache very many times for similar viewpoint changes. And here you can see our our caching approach achieves almost indistinguishable results from the baseline with a significant speed up of 1.8x. Importantly, in these 1.8x, the cache initialization times are already included. We perform automatic cache updates as soon as the viewpoints change too significantly or if cache hit rate decreases too far. The small spikes that can be seen here are due to cache hit rate decreasing and thereby performance decreasing, and as soon as the cache is reinitialized, performance is back to normal. So some conclusion, limitations, and future work. One limitation are currently large cache sizes, which make our method not suitable for lower-end graphics devices. The 3.4 gigabytes were for full HD resolution. Cache initialization is also a problem and would require significant latence hiding for real-time applicability. For offline rendering, this is of course not a problem. And our method is still slower than explicit methods, for example, meshes or 3D Gaussian splatting, while while not suffering from some of their downsides, like popping artifacts for 3D Gaussian splatting. Concerning future work, it's desirable to further reduce cache size, for example, by compression or hierarchical consolidation, so combining similar spatial latent codes inside the cache, and applying our method to VR applications where we can essentially reuse the same cache for two viewpoints. In conclusion, we are able to accelerate Nerfs by caching and reprojecting Nerf latent codes. We employed a fully view-aligned, fully volumetric cache and are able to re-evaluate view-dependent effects successfully. Also, our method enables high quality and fast offline as well as real-time rendering. Thank you for your attention. Our source code is public on GitHub, and please visit our project page for more information.
Thank you, Michael. Really good speed ups. While we're setting up the second speaker, do we have questions in the audience about this work? Maybe I can start with one. I know it's probably out of the scope of the work, but how would you compare in terms of the performance and memory footprint your method to Gaussian splats?
Yes, I think in terms of model size, instant NGP models, except for the very huge variant, compare quite well. So Gaussian splatting models can be exceptionally large. But in terms of memory footprint during rendering, Gaussian splatting is pretty efficient. And in terms of rendering times, also most Nerf models, except for the most efficient baked methods, can't compete really at the moment.
I guess as a follow-up, have you considered combining the best of two?
We tried a forward reprojection method that would probably go a similar path, but in the end we switched back to a backward reprojection process because it allowed us for better cache misdetections and filling in missing information inside our cache.
Thank you. Any other questions in the audience? Oh, yeah.
Yes?
Do you have to do any compensation for the variable length of the cache?
Can you repeat that?
In voxel space, your cache regions are not of uniform volume. You have to do anything to compensate the areas represented by
So we use a regular Voxel. I think the question was if our Voxel grid is if it is irregular or.
Well, as you get further out in the voxel space, each voxel represents a larger volume. So the non-uniformity of the regions that are being represented in the cache you have to compensate.
Yes. So essentially, our Voxel grid lives in a space where the Z coordinate is the index of the stepping space. You can read more in the paper, or we can talk about it afterwards. Essentially, yes, regions that are further away from the camera, we use exponential stepping, so we use larger and larger step sizes. And then by bringing it back into the stepping space, this contracts basically the space again, so you can properly trilinearly interpolate. I hope this answers the question.
Any other questions?
Yes?
Is there any disocclusion error? So usually the projection solution based on kind of the force of projected errors and kind of
So the question is if we encounter any problems due to disocclusions. And this is the nice thing of our method, as we perform per sample cache hit and miss detections, and as we know the exact known range of our cache, where we should have information, we are able to then resample with the help of the global previously defined occupancy grid and fully get rid of any disocclusion problems. I also, you can also try out our code, the real-time viewer, where you have a nice visualization of rendering without evaluating cache misses and with evaluation. That should also be in the supplementary video.
All right, let's have some time for the next speaker. Meanwhile, let's thank Mikhail again.
Thank you.
All right, and let's see if I can read the lines this morning. Our next paper is about converging algorithm-agnostic denoising for Monte Carlo rendering, and Elena Denisova will present the work.
Hello? Can you hear me? Okay. Good morning, everybody. So, as you may know, Monte Carlo path tracing is a rendering technique that is primarily used for offline video and image generation in the movie industry and medicine. The algorithm is iterative, meaning that the quality improves progressively with the growth of sample counts. The average of the samples forms a Monte Carlo estimate for every pixel. To address the problem of the excessive noise, some denoising can be applied to enhance the overall quality. However, even high-quality deep learning-based denoisers like optics or open denoisers often struggle to distinguish between fine details and the noise, resulting in excessive smoothing. This issue can be illustrated better in the visualization of the difference between the denoised images and the reference. Here, darker pixels indicate better results. Sometimes, especially in the scenes with a lot of fine details, denoising may even stop to improve the quality starting at some iteration. In such cases, the sequence of the denoised images even doesn't converge to the reference image. So it can be beneficial to actually blend the noisy Monte Carlo estimate with its denoised counterpart. The idea is to recover the fine details that can be missed during the denoising, meanwhile preserving the denoised areas where needed. Unfortunately, all the practical solutions proposed so far are deep learning based. It means that if the denoising algorithm changes, the model must be retrained. Moreover, these solutions require that the Monte Carlo estimate and its denoised counterpart to be obtained at the same iteration. That actually can be not efficient. We propose a solution that is free from these two limitations. So let's consider the following optimization problem. What we want to do is to blend noisy pixel n with its denoised counterpart d, so that the difference between the result and the reference image and the reference pixel r is as small as possible. Let's define the weight I of the noisy pixel n to be the number of iteration at which this noisy pixel was obtained. So we need to find a non-negative weight w for the denoised pixel. As the norm is not negative, the solution of this problem satisfies the following equation. On the other hand, the Monte Carlo estimate at the iteration k is the average of the samples obtained until the iteration k. And it is also true for the reference pixel because it's simply a Monte Carlo estimate obtained at some high sample number n. Let's substitute the first member of the sum by the definition of the Monte Carlo estimate. And then let's represent our denoised pixel value as the average of w different samples, which is actually the definition of the unbiased Monte Carlo estimate obtained at iteration w. Substituting the second member of the sum, you can actually see that the reference image, the reference value becomes the unbiased Monte Carlo estimate obtained at iteration I plus w. What does it mean? It means that instead of solving the initial problem, we can actually solve a simpler problem. And moreover, we can show that for the solution of this problem, the following equation is true. In other words, mean square error between the reference and the denoised pixel obtained at iteration I should be equal to mean square error between the reference and the noisy pixel obtained at iteration w. With this in mind, let's consider the convergence curves obtained for different scenes generated with Mitsuba framework. As you can see, all these curves can be approximated by lines in logarithmic scale. Moreover, if we know the convergence curve and we know the mean variance of the Monte Carlo estimate, we can easily obtain the number of iterations at which this Monte Carlo estimate was obtained. So, to solve our problem, we need to know just two things: the convergence curve and we need to estimate the denoised image. To do the first, we can just apply a least square regression to the variance of the samples. And to obtain the second, we can apply Stein unbiased risk estimator to obtain the estimator of mean square error of the denoised image. To make it work, two conditions should be satisfied. First, samples should follow a normal distribution, and second, denoising function should be at least weakly differentiable. However, the convergence curve of the individual pixel is a little bit different from the convergence curve of the convergence curve of the entire image, and the difference can be explained by the presence of the outliers. On the other hand, and you can see this from the formula for sure, the values of sure can be negative, which has no physical sense. So So we propose to apply a Gaussian blur for the estimations, and also to zero or to put to the magnitude values the negative values of Schur. And the reasoning about this and all the details you can find in the paper. So we applied our method on the pre-generated scenes with the Mitsuba framework, and here you can see the crops of the landscape and the San Miguel scene obtained with Open Denoiser and optics. Blended is our result, and the error, as you can see, is lower for the both cases. The same regards the mean square error of the entire scene. We also measured the flip score for the scenes. Flip is the score that reflects the human perception and actually evaluates the visual quality of the images with respect to the reference. Also here, as you can see, our method produces better results. We also compared our method with the recently proposed deep learning-based method, PDM, which stands for progressive denoising, applying open denoiser and RT. RT is the denoiser that is based on open denoiser, but it also considers the variance of the samples. Again, for these crops, the error is lower for our method. And for the entire image, our results are comparable or even better, especially at the higher sample counts, with respect to those produced with PD. Regarding the flip score, again, our method is comparable or better at the higher sample counts. These are two plots that represent the mean square error calculated for all 10 scenes produced with Mitsuba, that, like I showed before. And the graph with the dots represents the following special situation. The situation when the denoising stops at iteration 128. In other words, it means that we continue to blend the Monte Carlo estimates obtained at higher sample counts, but with the denoised result obtained at iteration 128. So you can see that even in this case, the results are better, and which is very important, the sequence of the denoised images converges to the reference. Here are the results of the mean flip score in comparison with the deep learning-based PD. As you can see, our method is slightly worse at the lower sample counts, namely until the sample count 16, but then becomes comparable or even better at the higher sample counts, as you can see on the right. We also applied our method on the recently proposed advanced realistic rendering technique for biomedical volumes. As expected, also in this case, our algorithm works. Another example. On NVIDIA RTX A4000, the blending algorithm we proposed takes about 32 milliseconds, in which open denoiser takes about 15 milliseconds, Schur calculation about 16 milliseconds, and the curves calculation takes less than 1 millisecond, together with some filtering if needed. Against 33 milliseconds that requires PD algorithm. Similar to deep learning-based methods, our technique is not free from the artifacts, and these crops are extracted from the exact scene of the Mitsuba scenes that I showed before and blended at random sample counts. As you can see on the scenes with a lot of fine details and at higher sample counts, our algorithm works especially well. But at lower sample counts and in the homogeneous zones, we can observe some artifacts. So, we proposed a fully analytical method to blend Monte Carlo estimates with their denoised counterparts. The method can be immediately applied on any denoising algorithm, deep learning based or not, and can blend the images that are obtained at different sample counts. The method can be applied during the progressive denoising or as a final step for the denoising of the non-fully converged Monte Carlo estimate. We saw that actually the results depend a lot on the quality of the denoised images estimation. So some better estimation based on recent works for sure calculation can be applied. As I told, we applied our method on the pre-generated images obtained at power of 2 sample counts. But the real-time blending can be very interesting because some interesting consideration about the convergence curves calculation on the fly or stop iteration for the denoising can be get from this application. And finally, our method can be applied on adaptive sampling, as the algorithm already gives you the weights that can guide the adaptive sampling process. Thank you. You can find the source code of the implementation on GitHub.
Thank you, Elena. Very good work, very good presentation. I would like, okay, the third speaker we have here. Yeah, do we have any questions in the audience?
Did you try your technique on more traditional computer graphics scenes?
What do you mean by?
Not medicine related or something.
Yeah, as the question is if I tried the algorithm on the traditional scenes. Yes, initially we tried our method on the Mitsuba generated scenes. Yeah. So the algorithm should be independent on the Monte Carlo path tracing method that you use.
Other questions? I guess I have one. You mentioned that the estimates might not work that well for lower sample counts. Do you have any ideas what would you need to modify in the method to make it work?
Yes, this problem is the result of the normal distribution of the samples. So when we have lower sample counts, the distribution is far from normal. And actually, I think the best solution is to not apply the method on the lower sample counts, makes your denoising algorithm to run, and then start to blend from like some or fixed sample count or some empirically found sample count.
Got it. Thank you. Any other questions? If not, then let's thank Elena again.
Thank you.
Meanwhile, I'll welcome the third speaker. The third talk is going to be about aliasing detection in rendered images via multitask learning. And Shuho Fan is going to present.
I'm Suho Fan, and let me introduce my work, Aliasing Detection in Rendered Image via Multi-Task Learning. And given a rendered image from a GAN engine, we can tell its quality through aliasing detection without needing a reference image. This process is known as non-reference rendered quality assessment, or we call non-reference RQA. And why do we need RQA? As 3D scenes become more complex, and how to balancing quality and power consumption is a critical problem. And RQA method provide a criteria to achieve this balance. Another advanced application is that RQA can use for like a variable rate shading, or we call VRS, which determine resource requirements for each tile in real time. And given a GAN rendered image, traditional RQA method require a reference image, as we can see on the right side, and to compute the metric like PSNR or SSIM for quality assessment. But here's the problem, that how to obtain the reference image. To obtain a reference image, we have to know something like critical data like 3D mesh, material, and lighting. Or we can sample through a high SPP ray tracer. But acquiring the 3D information is challenging, and using a high SPP ray tracer is impractical due to its time consumption. Therefore, we need to indicate the quality of a GAN image without a reference image, which is a non-reference RQA task. To solve this problem, we divide the GAN image into different tiles and determine the quality of each tile through aliasing detection. And the number of aliasing tiles indicate the image quality. And we focus on aliasing because they are a common and major issue in the rendered images. And most quality assessment work focus on the real-world image. Therefore, non-reference RQA research is limited, and no public label data set for this task. And the first and the only non-reference RQA method for aliasing detection was proposed by Pandian et al. At HPG 2018. And they proposed a simple CNN model and treat the rendered image like the real-world cases, and achieve accuracy of 17% on our testing set. And since there is only one aliasing detection paper, we have to explore other areas for inspiration. And we need notice a method in image restoration called FBCNN, which focus on JPEG compression tests using a multi-task architecture. And their model reconstruct compressed image and predict QA factor at the same time. And we adopt this architecture to our task, slightly improve accuracy to 73%. And just a little bit improvement. Yeah. And we observed that the artifact in FBCN and our work are quite different. FBCN target the JPEG compression artifact, which affect the whole image, as we can see the JPEG image right on the right side. And in our case, aliasing often occur at edge, which means it's a local artifact. So our architecture must differ to address this local artifact. And another observation about FBCN is that their multitask architecture also enhances the predictor, and a green block we can see there, and through the image space supervision during trainings. And we can discard the decoder part during inference time, maintain a robust predictor without any additional computation cost. So our goal is to design a multitask architecture for non-reference RQA task, or we call aliasing detection task here. And we also need to design a dataset generation pipeline, since no public dataset exists for this task. Here are key insights of our work. First, we designed a multitask architecture based on FBCN. And second, we include temporal information through motion factor, which can easily obtain from the GAN engine. And here's a contribution of our work. Our work proposed a novel multitask model for aliasing detection. And we also designed an automatic labeling pipeline for data training and evaluation. And our method achieved better results than other baseline, as we can see on the table here. And we show the demo video to compare our method with baselines. And the red patch, we can see there is a different label from model prediction, and the green patches indicate the matching labels. And the accuracy of our baseline would change. And baseline, you can see on the bottom of there, bottom row, you can see the accuracy was rapidly changed. In contrast, our method was stable and highest accuracy due to its temporal information. And in addition to quality assessment like PSNR and SSI we mentioned before, other work focus on different inputs like a rendered image or like video. And however, this work requires reference image, which are difficult to acquire during inference. And other work focus on aliasing reconstruction, like TAA or FSR2, and some use a neural network to solve this question. But our focus is on detection rather than reconstruction. Okay, our method utilizes the motion factor to swap the previous frame to the current frame and concave together to provide the temporal information. And our model proceeds through two branches, as we can see the blue block reconstruction branch and the yellow block classification branch, or we call prediction branch here. And our model takes additional information from the previous frame and predict and reconstruction simultaneously, with the prediction branch robust enhanced by reconstruction branch. And during training, the output of a reconstruction branch is fed back to the next frame, forming a recurrent architecture. But here's a critical question: that how can we ensure both branches integrate information effectively? The output of a predictor branch, you can see the confidence there, and we will further pass through several NLPs and then through the reconstruction branch, ensuring the reconstruction is based on the prediction. And the reconstruction doesn't predict RGB directly. And we can see the decoded feature will pass through a network called kernel network to reconstruct the final result. And the goal of the kernel network is to make the training process faster and stable. And decoded feature pass through the 1x1 convolution and softmax layer, and to predict some 3x3 filters. And the final RGB was computed by passing the inputs through those filters. And how does the kernel network work? The kernel network works because the filter value from 0 to 1 since the softmax layer, and the output kernel is sizes 3x3, which reduces the search space of the model. And moreover, the final RGB output is limited to transform inputs using existing information. Okay, to summarize our architecture, first, we incorporate temporal information through the motion factor. And second, our model performs multitask. A reconstruction branch enhances the prediction branch through the image space supervision information. And third, we use the kernel network to make the training process faster and more stable. And here's our loss function. Our loss function consists of 3 different losses. The first is spatial loss, which is a simple L1 loss for reconstruction task. And second is a temporal loss, which proposed by Thomas et al., which compute the temporal gradient of reconstruction frame and reference. And third, the BCE loss, or we call binary cross entropy loss, which for the classification. And to train and evaluate our model, we have to ensure the data set is stable and unbiased. And we set a 3-step generation process. First, we record a camera trajectory and save it into a CSV file. And next, we use the FSR2, as we can see, capture frame buffer, under capture frame buffer there. And we determine the labels by toggling the FSR2. And we remove the randomized factor like wind zone or particle system for the stable generation process. Then we will capture the necessary G buffers like RGB and motion factor here. And last, we crop the source image into small patches And if source image rendered with AA, or we call it rendered with SFR2, the patches are labeled as negative, namely it's non-aliasing patch. And if the source image rendered without aliasing, anti-aliasing, or rendered without FSR2, we further determine that the edge is on the patch or not. If edges are detected on the patch, that patch will be labeled as positive, namely it's an aliasing patch. Okay, here's an overview of our data set. We generate our data set from the Unity SS store, and we choose 4 scenes from it. And we use 3 of them for training tests and 1 of them for testing, ensure no overlap between the data set. And our baseline includes the first Aliasing Detection model by Pendian et al. And our backbone model, FBCNN. And the ROC curve shows that our method has a better classification result across in the thresholds. And we further verify metrics like F1 score and accuracy by optimizing the threshold. The threshold is selected the point on the ROC curve that has a minimum distance to the 0,1 point here. And as we can see in the table, our result achieved the highest score across different metrics, proving our method's improvement. And as our model is a multitask architecture, we visualize the reconstructed result showing improvement without compromising either branch. But we have to notice that our focus is on aliasing detection, not reconstruction. To further verify the benefit of temporal information and reconstruction, here we set a different setting, like we can regard the temporal information as an additional input since it had the previous warped frame as an input, and the reconstruction branch we can regard it as an additional model since we added for the image space superficial information. As a combination, we have 4 different settings here. And first is CRS only, which is a simple classifier using a current frame to determine aliasing or not. It's just a basic baseline for other settings. And we have the CRS recon, which add a decoder to CRS only. And we robust the classifier through the image space superficial information here. And third, we remove the reconstruction branch and add the temporal information called CRS temp, which we enrich improved inputs with temporal information here. And that is our setting, which combines the temporal information and the reconstruction here. And here's the result of our baseline ablation settings here. And the orange lines indicate the CRS only, and which is a baseline for other settings. And the green and the red line here indicate that both reconstruction and temporal information enhance the classifier performance, and combining these 2 elements achieve the highest score across metrics, like as we can see the blue line here, and demonstrate that our method effectively integrates both types of information here. And in conclusion, we introduced a multi-task model that improves non-reference RQA tasks and combining temporal information and reconstruction for better result. And we also propose a labeling pipeline for training and evaluation. And our work is limited to training and testing on the same render effect. We plan to expand different effects like twin shading or like photorealistic effects to verify our models for diversity. And we also aim to test dynamic scene in the future. Thank you for listening.
Thank you, Shao. Really interesting results, really interesting work. Do we have?
So some of the tiles were 64 by 64. Is there a specific reason for that? Or if not, is that changeable? And what happens if you change the tile size?
Okay.
Could you repeat the question?
Okay. Is that your question? Like, why we set the tile to 64 times 64? Right? Yeah. Okay. This is 2 main reasons that The first work, as Penny et al., is use the 64 times 64 here. And another reason is that the edge device like mobile phone, the maximum tile size is 64 times 64. So that's why we choose the 64 times 64 here.
I have one question from the author of the previous work who is watching us online. So he is asking, how do you make sure the metric doesn't learn what you labeled in the ground truth data set, but kind of, I guess for the future work, right, tries to learn more of a perceptually detectable flicker, which is, close to human perception. It's a kind of future work, open-ended question.
Can you repeat that?
I guess for the future, right? How do you make sure that the metric is kind of closer to human perception of aliasing?
Okay. This question is quite hard. Since the current metrics doesn't focus on the aliasing this artifact. So we cannot tell that SSIN or PSNR, those metrics can fit our human perception. So most of them you choose a CNN model, or we call neural network, to solve this question, to hope that can fit more to a human perception.
Got it. Thanks. Any other questions? With that, that's the last talk of the session, so let's have a coffee break and let's thank all the speakers again.
do we only think about ourselves? Oh yeah. The first time that I met you, I thought it looked so sweet. I stood around for the hills, beating a retreat. And when I heard you talking with that alluring sound, should have recalled the sirens and how that things went down. Living on the trenches, looking for a way to escape. You always cut me down like a dreamers with the grapes. Never mind how I tried to leave you behind. I kept falling in your net. Oh, I've been so blind.
All right, let's start the next session on volume rendering and systems. First up, we have gigavoxels, dynamic parallelism, starvationless voxel rendering, and production for large and detailed volumetric worlds. Walkthrough with Anton. Help me out with the last name.
Antoine Richard-Mose. Can you hear me all right? Yeah? Thank you for the introduction. So my name is Antoine Richard-Mose, and we're going to be talking about voxels. So what makes voxels an interesting rendering primitive? Well, first of all, since your geometry is encoded as a texture, anti-aliasing just becomes texture interpolation, so simple and fast. They also have well-defined LODs. Meshes LODs can be a real headache, especially for aggregate objects like trees, where they can really fall apart. On the other hand, voxel LODs are just downscale version of your images, so really simple and elegant. So they're just like 3D bitmaps. And finally, because of their very ordered structure, voxels are easy to ray trace using a form of ray marching. So if voxels are so great, why aren't they used more? Well, they have tremendous memory requirements. If you use just a simple dense grid, we want to be able to have gigantic worlds with high level of detail, pixel-sized voxels, all of that in real time. But there's no way that we could fit a single voxel level stored as a dense grid on a GPU memory. Locally, we don't need to store the whole level. We only need to store what is visible. So if we look at a typical scene here, well, first of all, most of it is empty. It's just air between objects. We also have lots of space that is taken by voxels that are inside objects that is never visible. We don't need that either. And we also have everything that is out of the view frustum and everything that is occluded. So we only have a tiny portion of what we started with that is actually needed in GPU memory. And in fact, if our scene is composed mostly of opaque objects, we shouldn't need more voxels in VRAM than pixels on screen, which is much more reasonable. So how are we going to achieve our goal of storing only what is visible? Let's start with the stuff that is either empty or inside, so sparse compression. For this, we rely on a smart data structure. The most commonly run are sparse voxel O trees. They can be really compact, but are quite expensive to access because you have to do a lot of pointer chasing to access the leaves. So instead, for our paper, we chose to use indirection clip maps. Clip map is similar to a mip map, but instead of each level representing the same area at different resolution, the levels all have the same resolution, but represent larger and larger areas, which is what we want for LODs. And yeah, clip maps are centered around the camera, so you need to update them when the camera moves. But we don't store our voxels directly in the clip map. We only use it as an indirection into a brick atlas, a brick just being a small chunk of voxels, typically 8 by 8 by 8. And that way, we don't have to store empty bricks. And so indirection clip maps are much faster to access because they only have one indirection, but much more wasteful in terms of memory. And there is also a nice poster comparing different voxel data structures. So if you want more information on this, you can look it up. And now for the harder part of what we want to avoid to store in VRAM, which is frustum and occlusion culling. For that, we can take a look at our predecessor, which was GigaVoxel by Croissant and colleagues. It used quite an original scheme called ray-guided production and LA recaching. So it viewed the voxel data structure as a form of cache to store the viewed voxels. And the decision of what to put in cache is made at render time during the ray marching itself. So you have two tasks, the render, the ray marcher, and what we call production, which is creating voxels and putting them in the cache. And the production is triggered by the ray marcher, and when production finished, the ray marcher can continue. So here's how the ray marching loop looks like. So at every step, we check the brick state. If it is in cache, we just sample it and step on. If it is empty, we skip it. And if it is absent, we request its production. And production can mean lots of things, from disk loading to procedural generation, or really anything that can generate voxels. So we have two tasks, render and production. Both of them can be done in parallel. But they operate on different domains, one on screen space tile and the other on bricks. So it is not that straightforward to map on a SEMD machine like GPU. And so here is how GigaVoxel works. It starts by rendering every pixel, start by tracing, recording missing bricks along the way. And when all ray tracing threads are finished, production of the missing voxels can start, and similarly, when production voxels finished, ray tracing can resume. And you alternate between those two steps until the image is complete. So as you can see, there is lots of synchronization points with this algorithm, which can lead to lots of GPU starvation. To better analyze this, we developed a custom tool that we call the GPU core timeline. What you see here represents a single frame of rendering with time on the vertical axis, GPU cores on the horizontal axis, and red meaning that a core is doing ray tracing, blue that it is doing production, and black nothing. And so you can see that we have starvation at the end of each job, and that we have a big section with lots of tiny jobs that we call detail, and this section is really inefficient. For those that might be interested, here is how our GPU core timeline is implemented. All it required is a global GPU timer, GPU core ID, and the ability to instrument your shaders. At the beginning of a shader, it allocates a timeline entry, records to it the shader type, core ID, and start time. And then at the end of shader, it records the end time, so it gives us an interval. And now at the end of the frame, another shader can parse all those timeline entries and create the displays that you see here. And it runs in real time. And so now that we know that our issue is one of starvation, how are we going to solve it? We propose to use dynamic parallelism. Dynamic parallelism is the ability to launch GPU jobs from the GPU itself, something that normally only the CPU can do. So it is particularly useful for workloads that are both dynamic and irregular. As you can imagine, it's quite a powerful feature, but it hasn't really been used much in the graphic community. Perhaps one of the reasons for that is its poor availability. On the compute side of things, on the CUDA and OpenCL, it's really straightforward to use. You can use the exact same syntax to launch kernels from the GPU as you would launch kernels from the CPU. But sadly, on the graphics API side of things, we don't have that luxury. Nonetheless, we can use persistent threads to fetch and put work on a work queue, so making our own scheduler in a way. And this approach seems to be used more and more. It was, for example, featured in Nanite, and it was also showcased yesterday with the HPLock presentation. And interestingly, the mesh shading pipeline also introduced a very limited form of dynamic parallelism, with the task shader being able to launch a variable number of mesh shaders, but you only get one level of expansion, so it's very limited. And so if we apply dynamic parallelism to gigavoxels, we can get rid of all those synchronization points. And now voxel production can start as soon as the array needs it. And similarly, as soon as the production is finished, ray tracing can resume. So, but of course, there is no free lunch. And with more concurrency comes more headaches, namely data races. So we have a possibility here for 2 rays to start the same production, and also here for 2 production to resume the same ray. And those can be solved by carefully using atomic operation. And I refer you to the paper for more information on this. So, and also with our new scheme, we have to think about how to know which rays to resume when a production has finished. With gigavoxels, they could just use a full screen pass, but we cannot do that. So we tried a lot of schemes using a memorization, trying to record which rays were waiting for which bricks, but it wasn't really working. So in the end, we just decided to try to relaunch all the ways that are covered by the B box, the screen space B box of the brick, and it worked much better. So if we compare the diagram, we can see that hopefully we should have much shorter frame times. And indeed, if we look at our timeline comparison, we were able to approximately double the performance. So we were able to eliminate the end of job starvation and really scratch down detail. And you can even see that there is some purple, which means that the same core is doing ray tracing and production at the same time, which is possible because of hyperthreading. And in absolute term, we get about 40 to 90 FPS on a RTX 4080 at a resolution of 1500 by 1000. So it's real time. And now I can do a short demo. If YouTube's want to. Yeah, okay. Can have better resolution. Yeah, okay. Oh no. Okay. Well, maybe 1080p was hopeful. Yeah. So, on the right, what you will soon be able to see is a real-time view of our GPU timeline. Yeah, okay. And you can see that there is lots of gaps, lots of starvation. It was working before. Yeah. Well, you can find the video either online or it is linked with the article. May I ask everyone to get off the Wi-Fi, please? Well, so what you are supposed to see in this video is similar to what you saw before on the timeline, just in real time. After that, it should switch to the dynamic parallelism version, and you can see that the timeline is much shorter. There was also nice debug views showing bricks and voxels. But yeah. Yeah, this is a view of the voxels. Each color is a different voxels. And here compression is not doing it justice, but we achieved our goal of 1 voxel per pixel. And lastly, I will try to show you the cache updating. Well, I do the conclusion slide, and then I'll try to wait for the video to load while we answer questions. So the conclusion, limitations and future work. For limitation, we were able to greatly reduce the frame time, but they are still really inconsistent, which is not great, really spiky frame time, as you can see here. Also, we used CUDA for the dynamic parallelism, and it required a full gigabyte for its data structures, which is not great. Also, because of our brick B-box rasterization technique, we can only do primary ways, so it is limiting. And lastly, we used procedural generation for voxel production, but it is not clear how we could apply disk loading with dynamic parallelism, as currently we don't have any way to initiate disk loading from the GPU itself. And for future work, we would like to try to do a custom dynamic parallelism implementation using persistent threads. Maybe also try to look at cache prediction to smooth out frame times. And lastly, we would like to develop our GPU course timeline tool and make it portable and available for everyone. So thank you for your time, and I'm now ready for questions.
Questions for Anton?
Yeah, so the question is, if I understood correctly, what is the difference between dynamic parallelism and word graph, or could you apply word graph to this problem? Yeah. So from what I understand, word graphs are not able to be as dynamic as dynamic parallelism. You need to declare in advance what path it's going to take, but for us, the graph can be really deep and really dynamic. We don't know which way is going to need which brick. So I'm not sure if it is possible to use word graph. I tried to use CUDA word graph, but it wasn't really working. Yeah, I will look more into other word graph APIs. Maybe there is something to do here.
Have you thought of extending this to volume path tracing, maybe Woodcock sampling or something like that?
So it is a form of volume path tracing, because voxels can be semi-transparent. What was the second part of your question?
Something like real path tracing, where it's not just breakcasting through the volume, but actually doing Woodcock tracking or something similar.
I'm not familiar with the Woodcock tracking.
Okay.
Sorry.
Oh, no problem.
Oh,
So I have a question. So is this dynamic parallelism, is there a way to spread this across multiple GPUs, since this is GPU centric? So can you scale beyond a single GPU?
I don't believe that the current APIs allow us to do that. Our goal is to do real-time rendering, which usually doesn't work well with multiple GPUs, or it seemed to have been a bit abandoned the last years. So I'm not sure, but Maybe you thought about one GPU doing ray tracing and the other doing production. Yeah, haven't looked into that.
Any other questions from the audience? Let's thank our speaker again.
Thank you.
So next up, we have Thibaut Tricard, interval shading using mesh shaders to generate shading intervals for volume rendering.
Thank you for the introduction. I'm going to talk a bit about volume rendering and hardware acceleration. So first, volume rendering is something that is very popular in computer graphics. It can be used for data visualization or representing computer-aided design scene, but also for typical oil rendering with rendering of cloud, smoke, and other type of effects. There is many ways to do so. One of them is marching. There is also many approach to marching and representation of data. One of them is implicit surfaces. So the idea is that you represent your surface by a function or a signed distance field or procedural noise. It's usually quite costly to evaluate, but it has the advantages of having a very low memory cost, as the functions are typically easier to store than plain voxel or triangles. However, it's quite difficult to animate, and it has a poor workload balancing, and by that I mean that usually all the work is done by a single shading stage, usually a fragment shader, but it also can be a compute shader. When it comes to voxel, it's a bit similar. It's an explicit representation, as my colleague presented just before. It's quite easy to evaluate, but it requires complex memory management. But it's also very hard to animate. And once again, fragment shader or compute shader is doing all the work. And we don't really use much of the hardware accelerated feature of the GPU there. You can also try to accelerate that using acceleration structure. So here I took the example of bounding volume hierarchy. It limits the computational cost using pre-computed hierarchy. But the hierarchy evaluation is not free. It's quite hard to animate because you have to reconstruct your hierarchy if objects move too much. And also, once again, the hierarchy is evaluated by the fragment shader or the compute shader. And one other type of method I wanted to look at is surface-based volume rendering. So by that I mean all the peeling approach. So basically you render multiple times your scene, and each time you store the fragment you first meet, and then you do it once again by ignoring the fragment you already met. And it helps you create depth intervals that you can reuse afterward to do your volume rendering. Problem of that is that you have to store multiple frame buffer, which can be quite costly. It does not always work with overlapping geometry. It can create weird artifacts. And however, this has a more balanced workload because we are using the rasterizer, the fragment shader, vertex shader, and everything. So in summary, I showed two types of approach, marching-based and surface-based. So marching-based has the advantages of being low memory. However, it's high computational cost, poor workload balancing, and very hard to animate. In comparison, surface-based are very low computational cost. They are quite good at workload balancing and easy to animate. So if we focus on this type of approach, we can see that all the advantages come from the fact that we are using hardware accelerated primitives there. And the only drawback comes from the fact that we have to reconstruct all the depth interval in the post-process. So the question I wanted to ask during this work was, can we use volumetric hardware accelerated primitive in the rasterization pipeline? If we look at what we have access to vertices, edges, and triangle, but nothing in 3D. And ideally, we would like to have access to tetrahedron, but it's not the case. And one of the reasons why this is not the case is because when you look at simpler primitive, its screen space projection is always a fragment with a fragment coordinate, a depth, and all the attributes that come with it. And then this result is sent to the fragment shader that does its work. In comparison, if we were to do the same kind of operation on 3D primitives, it would create an interval because we have both a front and back face with a single fragment coordinate still, but two depths basically, and then two pairs of attributes after that. And if we were to dream about this ideal volumetric pipeline, it would take as an input tetrahedron with vertices and indices as we do typically for surfaces. This tetrahedron will be sent to the rasterizer, and then all of that will be solved by an interval shader that will replace the fragment shader. But as I said, we don't have access to tetrahedron. So question is, can we bypass this? So my hypothesis when doing this work was maybe you can use an early stage fragment to encode the tetrahedron such that the rasterizer be coerced into computing this projection that we want, and then getting our result in a fragment shader. So typically, early stage of the pipeline only handle hardware-accelerated primitive. However, recently, mesh shaders were added to the pipeline, and they can handle arbitrary geometry and in a very complex way. So maybe there is something to do there. But to understand how we can coerce the rasterizer into computing what we need to understand how it works. So first, let's say we try to rasterize a single triangle. The rasterizer will, for every pixel on screen, will try to decompose it into screen space barycentric coordinates that represent the position of the point with respect to the vertices. And then using that, it will recompute the depth using a very similar equation here, but just using 1 over the depth. So now that we know that, can we actually generate depth intervals? To understand how it works, we have to focus on a much more simple case than tetrahedron. And this case is what I call the prismoid. So it's just two triangles that project exactly on the same pixel in screen. So here you have two representations, one in projected space and one in camera space. For the remainder of this presentation, I will focus on the projected space as it simplifies the equation quite a bit. So as we have a couple of points that are equal in screen space, we can define these equalities there. And using that, we can reapply the same equation that would apply the rasterizer to both triangles. And we can see that actually we can use the same set of screen space barycentric coordinates to represent the same point on both triangles here. And so by just following the same method, we can compute two depths using the same set of barycentric coordinates and with just this equation here. So now the question is, how can we force the rasterizer to compute these two depths, and how can we have our results? Well, the solution is this one. You encode your two triangles as a single one, which will be used as a proxy, and you just encode x and y for the position, and you leave z to 0. And this will force the rasterizer to use screen space barycentric coordinates to interpolate vertices attributes. And then you just set up your vertices attribute as 1 over the depth of the 2 points. And then once the rasterizer will do the attribute interpolation, it will recompute these two depths. Finally, when you arrive in the fragment shader, each fragment shader invocation will receive two depths, so 1 over the depth of the front faces and the depth of the back faces of this peculiar shape. So now we have a big problem. Not everything is made of prismoid. And so now I'm going to explain how we can generalize that to tetrahedron. So to generalize that to tetrahedron, we have to reformulate a bit what we want as a properties for our mesh. So basically, we want to remesh the tetrahedron such that for each front faces, we have exactly 1 back faces. And to do so, actually, it's not that difficult. You have to separate the front and back faces, and then you have to recombine them in a merging operation that will create new vertices, new edges, and new triangle. You can find more information about this merging operation in the article. And actually, for the tetrahedron, it can be solved analytically. And there is only 2 cases. One case is where the tetrahedron presents as a footprint of a triangle in screen space. And in this case, you can only create 3 prismoids. And one other case where it presents as a quad in screen space, and then you have to create 4 prismoids here and 4 triangle proxy. And then you encode your geometry, as I mentioned earlier, for the prismoid. So x and y, and that's z to 0. And then you encode the front faces depth and the back faces depth. Finally, if we summarize our pipeline, as an input, we have vertices and indices that represent the tetrahedron. Then we have the mesh shaders that apply transformation, animation, and then encode the tetrahedron in a way such that the rasterizer will be coerced into solving the screen space projection of the tetrahedron for us. Finally, the fragment shader receives the depth intervals, so the depth of the front and back faces, and can do its shading in this band. So it works for a single tetrahedron, but it also works for an arbitrary number of tetrahedrons. And now if we focus a bit on what's happening in the fragment shader. So if we check this very simple scene, so we have 3 tetrahedrons, it's a cut view here. What we have is for each pixel, we trace an array, and we can see here that we have 3 intervals appearing. And these 3 intervals will be shaded separately in 3 different invocations of the fragment shader. And the fragment shader can compute optical depths or remarching within each of these intervals. And finally, results are merged by the blending stage or by the depth buffer stage. And what's interesting with this method is that if you have, for example, if you are doing, for example, a remarching operation, you may be aware of that remarching can be quite costly, mainly due to grazing rays. And here, in this case, for a single array, it will be divided in 3 separate intervals. And here, the grazing part of the array will be solved in a separate fragment invocation than the other parts. So it will reduce a bit the computational toll here. So now let's have a look at some results. So here are the 2 results I already showed. So here you can see the wireframe and the optical depth computed in a single pass of computation. But it can be also used for more complex objects, such as this one here. So here we can see we have a crystal that is rendered. And we can see that we have many overlapping parts in screen space that are correctly rendered in a single pass while being transparent. Our method actually supports using multi-channel optical depth. So if you want to render complex objects, so here you have 1 color per tetrahedron, and then you can easily compute the transmittancy, and you can mix that with of map or any other effect you want. Right. So our methods support animation and intersecting geometry. So here you have an example of a complex system where the PAL is rotating, and then we create an exploded view of that. All of that is done in a single pass of rendering here. And we don't have to reconstruct any acceleration structure, as we are using just plain old tetrahedron there. Also, I didn't mention that, but by a clipping operation, we are able to put the camera even inside of the object without having many issues here. It costs a bit more, but it's doable. And finally, I mentioned earlier that we can do marching with our method. Here is an example. So I didn't put the video because encoding was a bit shaky on this one. So here you have 10,000 asteroids that are computed using an hypertexture each. And each of them is bounded by a tetrahedron, and so we compute each asteroid within the bound of the tetrahedron here. So here I put a summary of the performances of our method. So we can see that even with a very large number of tetrahedrons, such as the jet engine I showed, we remain real time, and even more than that, while being rendered in 4K on a RTX 4080. So finally, if we summarize, we proposed a tetrahedron rasterization method that can do single-pass, accurate, transparent rendering. It can also be used for unordered volume rendering that support animation without needing to reconstruct any acceleration structure. Currently, this only works for unordered volume rendering, as intervals are solved separately and then blended just using the blending phase. But it could be potentially solved in future work using a peeling-like method, for example. Another limitation is that we only handle one tetrahedron per work group in the mesh shader at the moment. This might be just due to our implementation, as we do not yet have access to meshlet for tetrahedron that we have for surfaces. And so loading multiple tetrahedron might have had an issue while testing. Finally, we do not support per vertex attributes interpolation in the rasterizer. So I mentioned that we put z to 0 while encoding our tetrahedron, and this prevents us from doing correct interpolation of UV or texture code or normal or other stuff. So it might be solvable in the future by computing it in the fragment shader, for example, but it's still not really look like that. And finally, I mentioned animation. I only showed here animation, rigid animation, mainly due to the fact that TET mesh with animation weights are hard to find. And so I was not able to test if it was working or not. But there is no theoretical reason for it to not work with animation weight. So that's it for me. All the source, here I put the link to the source of much of the example I showed. If you have any question, just ask them.
Questions for Thibaut?
Yes.
I'm not sure if I missed it, but how do you obtain the tetrahedrons, for example, for this bunny? Where do you get the tetrahedrons from?
Oh, so the question is about how do we get tetrahedron meshes? I just use TETGen. Okay.
So I noticed in your results the kind of the frame rates weren't linearly, we're not in line with the number of TETs. So why were some kind of higher TET models actually faster than the lower TET models?
Okay, so there is two things. I separated asteroids there. It used less states, but each state represents a marching invocation, so it's a bit more costly. And for the rest, it's a bit hard to know exactly why. One of our hypotheses is that we tend to, in some cases, saturate the blending phase, because usually we just emit one or, let's say, 10 fragments per pixel at the end, but here with the number of tetrahedron we have much more fragment per pixel to solve and to blend at the end. So it might be just that, but I'm not actually sure of the reason why here.
Any other questions? All right, let's thank Thibaut again. All right, next up we've got Daniel Meister.
Is it working? Yeah, great. So my name is Daniel Meister, and I will present our new ray tracing framework, HPRT, which is a ray tracing framework tailored for AMD GPUs, and we are focusing on professional rendering. So we have advanced rendering features such as multi-level instancing, motion blur, intersection filters, and others. As a core acceleration data structure, we use bounding volume hierarchy, BVH, which provides scalable construction. And as a minor contribution, we also proposed a new BVH construction algorithm using spatial splits on GPU. HipRT is cross-platform thanks to HIP, which is a kernel language syntactically almost identical to CUDA, but it can be compiled also for AMD GPUs. It runs on both Windows and Linux systems, and HipRT can run also on GPUs without hardware acceleration compared, for example, to Vulkan or DirectX, which might be useful, for example, on MI GPUs, which might be useful for scientific computing, for example. The code base is relatively small, less than 20,000 lines of code, and this is thanks to HIP, and HIP supports modern C++ standards, so we can use all these nice modern features such as templates, lambdas, and other constructs. And last but not least, it's open source. HipRT was already integrated into several renderers, so the most famous one, Blender Cycles. Next, we have PBRT4, version 4, which supports also GPU ray tracing, so we implemented another backend in HipRT, very popular research-oriented or educative framework. And the last is our Radeon Pro Render. So we are not limited by standards given by third parties like DirectX or Vulkan, so we can design our own API, so we can focus really to make it very easy to use. Yeah, this is very sensitive topic, I would say, but we believe that ray tracing pipeline is not very, programmable pipeline is not very suitable for professional rendering. In general, it is opaque and difficult to debug. Shader binding table is a very difficult concept to grasp. There are whole chapters explaining how to set it up. And for professional rendering, it's not suitable because it couples ray tracing and shading. And shading is typically way more complex in professional renderers. So yeah, it's great concept for real-time ray tracing, like games. So it's like natural transition from rasterization pipeline, but not that good for professional rendering. It's a kind of artificial construct. Yeah, so HipRT follows similar philosophy as Embry, so we want to have a minimal host code setup, unlike Vulkan, for example. Yeah, we are providing just ray tracing functionality. All other computations are on the application side. So, for example, shading and also data assignment, which is in other APIs done through shader binding table. We really cannot avoid custom functions. We need intersection functions for custom primitives, and the second type we have is intersection filters that I will explain later. Yeah, but in our case, it's just 2D table. One dimension is ray type, and the other dimension is geometry type. Here you can see minimal example of HipRT API. On the left side, we have the host code set up, or just part of that, where we create triangle mesh defined by indices and vertices. Then we create HipRT geometry, which is BLES in HipRT. We build it. So in this example, we have just one level hierarchy. And the last line is kernel compilation, trace kernel compilation. In this case, we use runtime API, but it can be done also offline. On the right side is the corresponding trace kernel, which is nothing else than standard HIP kernel with injected HipRT functionality. So we first create ray. This is on the application side. Then we create HipRT traversal object passing the geometry and the ray, and then we find the intersection. And again, how the result is used is on the application side. So as I mentioned, as a core acceleration data structure, we use BVH. We have 3 options, quality options, like fast build, balanced build, and on the next slide, high quality build. Fast build is implemented as LBVH, very fast construction algorithm based on sorting geometric primitives along the Morton curve. And after the sorting, we can easily extract this implicit BVH given by this sorting in a single kernel launch. But the quality is not that good because we don't optimize the surface areas of internal nodes at all, not explicitly at least. So that's why we have a balanced build, which is still relatively fast, but yet the quality is much better. It is a bottom-up, iterative, bottom-up. Yeah, our implementation is based on block algorithm, parallel locally ordered clustering. It is a bottom-up approach, building BVH iteratively, where in each iteration we merge multiple cluster pairs. Our current implementation is based on block++, which is optimized version of the original algorithm using a single kernel launch per iteration. And yesterday you might saw HBlock, which is like the next evolution of this algorithm. So we plan to replace our current implementation by HBlock very soon. And in this algorithm, we use also like Morton curve, but to find the nearest neighbors for the clustering. So in this case, we really optimize the surface areas of internal nodes. So the quality is much better. The last option, high quality build, as you can guess, it's if you really aim at highest possible quality at the cost of higher construction times and also like higher memory consumption. Our algorithm is based on the SBVH algorithm originally proposed by Stich and colleagues. Originally it was just a single-threaded CPU algorithm, and we tried to reformulate it for GPUs. The motivation is that the standard BVH doesn't go well with long diagonal triangles. So what we can do is to use spatial splits, which is a technique known from KD trees. So we can achieve tighter bounding boxes, but the cost is that now triangles are referenced in both subtrees. So SBVH is like a top-down approach where we try both standard splits and spatial splits, and we select the one minimizing the SAH cost approximation, which takes into account not just the surface areas, but also the number of references in each subtree. And yeah, our goal was like preserve the quality of the original algorithm, what we achieved, but yeah, the construction times are way higher than like the fast and balanced options. The last option is not a builder, but it's like API custom BVH import that allows user to import his or her own BVH to HPRT and then use the traversal code, which is I think useful for example, research. Now I would like to talk a bit about features we have in HPRT. The first one, multi-level instancing, which is generalization of two-level hierarchy into more than 2 levels. We support basically arbitrary number of levels. We need like additional logic, like so we need like a short additional stack to store the hierarchies above, to be able to go from hierarchy, bottom level hierarchy to hierarchy above. And also we need to get the array in that corresponding space. And advantage of this feature is that it can like reduce memory consumption significantly. So for example, we can render Moana Island on a single GPU in core, which is very like, it's a huge scene with 156 million unique primitives and 31 billion instantiated primitives. And this is from the PBRT port. The second feature we have is instance-based motion blur. It is multi-segment motion blur with non-uniform intervals. Multi-segment means that we have multiple keyframes for each instance. And non-uniform intervals means that we can specify the time for each keyframe. So for example, we might have 3 keyframes with times 0, 0.1, and 1. So like you can achieve similar result in optics, but optics supports only uniform intervals, so you need to manually resample into 11 keyframes. The second thing is that we support like correct interpolation even when we use matrices, because we internally decompose matrices into individual components and then we interpolate them separately to get, especially the rotation is the most problematic. To get the correct result, you need to do spherical quaternion-based interpolation. If you interpolate just matrices, if there is no rotation, it's I think okay. But if it includes rotation, you might get like incorrect result, and also like even like singular matrix. Ray traversal use stack-based algorithms, so nothing special. One unique feature we have is that we can specify this traversal stack as a template argument in the traversal object. So we have like 3 predefined stacks from very simple ones, which are easy to set up, to more complex one like this global stack, which provides better performance, but it's slightly more complicated to set it up. You need to manually pass the buffers. And this stack combines shared memory for topmost entries and as a backup global memory for bottommost entries. Yeah, intersection filters that I mentioned before is a second type of custom functions we have in HPRT. And this is an optional custom callback that allows user to filter out some of the intersection, which is useful, for example, for alpha masking or filtering out of intersections. In programmable pipeline, you can achieve the same result, but you need to use any hit shader even when you want to find like the closest hit, which is like a bit unintuitive, at least for me. Yeah, so far I talked about features and API. Now let me also show you some numbers. So performance comparison. For that purpose, we implemented waveform path tracer, which is nice because we can like separate ray tracing and other computations, so shading. So we can switch different ray tracing implementation while keeping shading the same. We have 2 settings for the scene partitioning, so original 2-level partitioning, which is the more practical case, and the second setting is like pre-transforming everything into a single large instance, which is useful for evaluation because we have one a single SAH cost and a single build time. And we have 2 ray tracing backends. One is HPRT with 3 options, and also to demonstrate that custom BVH import feature, we built the BVH on using Embry on CPU with high quality setting and spatial splits, and then we import it through this API to HPRT, which is like, besides demonstrating this feature, it is also very good reference method. And for second backend is Vulkan. There are only 2 options, fast build and fast trace. And all tests were executed on AMD Radeon Pro W7900. Here you can see our test scenes. So they are like quite complex, both in geometry and also light transport. So you can see various global illumination phenomena, such as glossy reflections, indirect shadows, and others. So here you can see average relative trace times. So like to average over all scenes. So first we need to normalize them to get meaningful numbers. For that purpose, we use the block, the green one, so it is always 1. One observation is that the Vulkan is faster for primary rays, but way slower for shadow rays and slower for secondary rays. So HPRT is faster for shadow rays and secondary rays, and it is also faster. Our SBVH is also, what is interesting, is faster than that imported Embry built BVH, so that's also interesting observation here. So SBVH is pretty good, but there are the build times are way higher, like more than five times higher than for other builders. But this is not like a big problem, as you will see on the next slide. If we reuse the BVH many times, which is the case in the professional rendering, this becomes marginal. So here you can see build time and average build time, again normalized by block and SAH cost. So LBVH is the fastest algorithm overall, followed by block, which is interestingly faster than both Vulkan options. And SBVH is slow, but it provides like the lowest SAH cost, practically the same as Embry imported, like BVH built by Embry imported to HPRT. This is time to image, which is build time plus trace time for one particular scene. For other scenes, it looks similar. On x-axis, you can see samples per pixel, and at 0, it is offset by build time, so like initial overhead, which is higher for SBVH, but SBVH has higher quality, right? So the per sample overhead is lower, so with increasing number of samples, at certain point it becomes faster than other methods, and in this particular case it is like 64 samples per pixel, which is still pretty good for professional rendering because we use much more samples, right? So to conclude my talk, HPRT is a new open source ray tracing framework tailored for AMD GPUs. Performance is comparable with Vulkan, maybe slightly higher. I think API is definitely more user-friendly than Vulkan. SBVH provides very good acceleration, ray tracing performance, but the construction is slow. So that's also like one of the points for future work, like to improve the construction speed. It is tailored for professional rendering, so we have these features like motion blur, multi-level instancing, and others. We also pointed out some of the drawbacks of existing APIs, but this is rather minor. For future work, we would like to integrate HBlock, which was presented yesterday. It would be also interesting to introduce new primitive type, curve, so optimized primitive for hair or fur, and also our current implementation is hopefully correct, but there is definitely room for optimization, especially of these advanced features like multi-level instancing. So that's all. If you are interested in HPRT, you can use this QR code or these links. Thank you for your attention, and I'll be happy to answer any questions.
Questions for Daniel?
Yes, I can yell. So you use for a query. Do you think shared execution in ordering would be useful? And how would you do it if you do a query?
Can you repeat the question?
Question is that shader reordering would be useful, and how to do it if we use ray query. That's a good question. Like, yeah, basically shading is on the application side, so you can like use it after the ray. So shading is invoked after you find the intersection, right?
It's okay if you don't have an immediate answer.
Like, yeah, I don't know right now. I don't know right now. Sorry.
So you have mentioned Blender. Is it already part of Blender, or how can I get my hands on it?
The question is whether the Blender is Blender integration is part. Yeah, it's already part of the Blender. I'm not sure like whether the stable release, but at least yeah, it's in the official repository.
In your slide said that your SBVH implementation was GPU-based, top-down, and did spatial splits. Is your top-down approach, is it like one kernel launch with a span of all the triangles in the scene, and that does one level of partitioning, and then another kernel launch for the next level partitions and so on?
Oh yeah, so the question is about SBVH implementation. Yeah, it's very like, I would say naive, yeah, so it's like one kernel, it's like several kernel launches per one iteration. Okay. Actually, like, yeah, compared to standard top-down build, it's like, yeah, there are a lot of like caveats with spatial splitting.
So one thing I think that would imply, versus the single-threaded CPU-side SBVH from 2008, is that you spend your spatial split budget on the root nodes and near the top of the tree, which is more efficient than the original SBVH paper, right? If you have this much additional memory allocated for your spatial splits, and you do the splits at the root node, you're decreasing the size of massive AADBs, right? And then you gradually fill up that space, and then when it's gone, that's well before you've reached your leaf nodes. Whereas in a single-threaded SBVH, you're burning that budget down at all levels of the tree. Have you noticed that, and any speed up from that?
Yeah, this is a good question. I think in the original like algorithm CPU version, you don't have like a strict budget, so like you can allocate memory as you want, right? But yeah, in our implementation, it's like that you use like 1.5 of the inputs of the number of triangles, for example, and you allocate and you use it, yeah, until it's like full. So yeah, but I think it depends on in the original algorithm. It depends like what you use for if you use stack or queue, right? If you use queue, it would be similar, I think.
Yeah, in the paper they use this stack, right?
Okay.
So it was a depth first traversal.
Oh, okay.
Okay, so it sounds like.
But I think there is no like strict budget in the original algorithm. It's like that you like stop. You stop when I think the like intersection of both like of the children is like less than some predefined threshold. Yes.
Thanks.
Any last questions for Daniel? Okay. Let's thank the speaker again. And that was our last talk of the session, so on to lunch.
The day will come when you first realize what you have done, and you finally get your debt repaid and revenge is served on a cold plate. Oh yeah, on a cold plate, on a cold plate, on a cold plate. other guys riding on backbiting and get away with lies. No matter what it takes, who is gonna cry? The only thing that matters is you get what you decide. But I know for sure the day will come when you first realize what you have done, and you finally get your debt repaid and revenge is served on a cold plate. You hear the roll of the shutdown when the world will stop without a sound, and the moment you will cry for help, that we only think about ourselves. Oh yeah. The first time that I met you, I thought it looked so sweet. I stood around for the hills, beating a retreat. And when I heard you talking with that alluring sound, should have recalled the sirens and how that things went down. Living on the trenches, looking for a way to escape. You always cut me down like a dreamers with the grapes. But never mind how I tried to leave you behind. I kept falling in your net. Oh, I've been so blind. But I know for sure the day will come when you first realize what have you done, and you finally get your debt repaid and revenge is served on a cold plate. And you hear the roar of the shutdown when the world will stop without a sound, and the moment you will cry for help, and we only think about ourselves. Oh yeah. About ourselves. About ourselves. But I know for sure that day will come when you first realize what you have done, and you finally get your debt repaid and revenge is served on a cold plate. Oh yeah. On a cold plate. On a cold plate. On a cold plate.
Anything? Test. If you could take your seats, let's get this party started as soon as we can. I mean the next session of this party. It's already been a party for a day and a half, right? Okay, let's dive in. I'm Dave McAllister. I'm chairing the next papers session. This session has 3 talks on effectively compression of user-generated content for the GPU. One of those compresses it by procedurally generating it on the fly. The first paper is by Gustav Valdemarsson and Michael Doggett, both of Lund University. And Gustav is also full-time at ARM in Sweden. And it's called Succinct Opacity Micromaps. So Gustav will present.
Thank you. Let's see, can everyone hear me? Yes. Thank you, Dave, for that nice introduction. And thank you, everyone, for coming. And now I have the important and difficult task of bringing everyone here again after the town hall and after the actual buffet again. So allow me to start this session off by introducing you all to the concept, or rather reintroduce you all to the concept of micromaps. So to start things off, let us have a quick look at what I will actually present. In short, I have 3 main topics that I want to go through. And they are a quick overview about micromaps, and of course opacity micromaps in particular, including a new micromap indexing algorithm. Then we will proceed through to discuss our main contribution in this paper, a new method for compressing micromap data by converting it into a densely packed tree format. But more on that in a little bit. Then we will round things off with a frame time performance evaluation of the above format, as well as many other formats used to perform opacity testing, including the official micromap formats that are now accelerated on hardware on modern NVIDIA GPUs. But without further ado, let us jump straight into the topic and talk about the micromaps themselves. What exactly is it? In short, it really is as simple as an array of values that has been mapped onto fixed sub-areas of a triangles that are specified by a space-filling curve. In theory, we could actually assign any kind of data to these particular sub-triangle faces. But for opacity micromaps in particular, we only care about 2 or 4 values. Consequently, these values only occupy either 1 or 2 bits each. Hence, the opacity micromap is typically handled as a type of bit string. And semantically, the values it contains are mostly self-explanatory. Fully transparent or fully opaque means that that particular sub-triangle face is either completely opaque or transparent in a ray tracing context, whereas unknown values means that we should use some other method to perform the actual opacity testing. For instance, by calling the AnyHit shader in the ray tracing pipeline and looking it up in an alpha texture. Additionally, these values also have a 4th value to allow you to convert it back into a 1-bit state. For instance, when you want to reuse a particular micromap in an algorithm where you don't actually want to call an AnyHit shader, such as when you are using shadow rays. Starting from the beginning, though, micromaps were originally invented in order to improve the performance with these AnyHit shaders. Simply put, by using a little bit of extra memory as input to the ray tracing pipeline, you could improve performance by reducing the number of times you would actually have to call the AnyHit shader by around 30 to 40%. And this concept has remained more or less constant in the current form of opacity micromaps that have found their way into the Vulkan and the DirectX API. The main difference is simply how the subtriangles themselves are ordered in the final bit stream, which you can see in these examples here. In the original format, the triangles are ordered in strips, going from the W coordinate in the left corner, going towards the V coordinate at the top. Whereas the current format walks across the subtriangles themselves in a bit more even fashion, very similar to how the C-curve orders tiles. One notable consequence of this, however, is that the original format is technically more granular, as each new subdivision level only really adds another strip. Whereas, However, the negative part of this is that similar to data stored in row or column order fashion, this could lead to a somewhat unbalanced caching behavior depending on how you would actually access the micromap itself. And this then naturally begs the question, how would you actually look up a value in the micromap? Which, as if by coincidence, leads us to our first contribution. A new algorithm to kind of explain this mapping of barycentric coordinates to a micromap index. So, starting from the beginning, you have your triangle, and then you divide this at each of the midpoints, at the exact midpoint, thus forming 4 new subtriangles, which I have taken to calling the left, middle, right, and top subtriangles, which are also indexed, as you can see in the corner there. Then, by using a little bit of geometry, we can then derive equations to link together these midpoints and the vertices. And furthermore, we can express each vertex and midpoint using barycentric coordinates. And with a little bit of substitution, we can then find expressions that lets us use the original barycentric coordinates to update them again to any of the particular subtriangles. And we could then use that and repeat it recursively to any desired subdivision level to find the particular index of the particular subtriangle face index that we're interested in. There are a few more details to this though, but those details only really apply to the literal edge cases to ensure that rounding is correct. So if that's of interest to you, please see the paper for those details. Which then leads us on to our main contribution in this paper, the compression algorithm itself. As I worked with opacity micromaps, I found plenty of cases where large swaths of the map would contain basically the same value. Some examples you can see here from this text, from this small texture atlas from our good old sponsor scene at 3 subdivision levels. As such, I looked at the indexing mapping algorithm from before and thought, you know, wouldn't it be a good idea if we didn't have to go all the way down through the call stack to the subdivision level that was chosen to actually find that value, if we know that all of the values beyond a certain level is going to be exactly the same? That is, couldn't we have some kind of marker that tells us that you're not going to be able to find anything new beyond this point? And that is more or less what I did. I converted the micromap into a kind of 4-way tree structure, where each node represents the area of all underlying subtriangles, effectively mimicking the call stack of that previous indexing algorithm. And of course, as we've already seen in a few earlier sessions today, there are a couple of ways of representing such a tree. We could do it implicitly in an array, very similar to how we typically represent binary tree, or by using pointers. Storing the tree implicitly would be ideal, of course, because then we don't need any extra data. However, the trees that we are going to handle are typically not going to be balanced, so this would potentially lead to a lot of waste storage. Pointers, of course, could handle this particular aspect better, but at least for opacity micromaps where the values we care about are so small, bringing pointers into this felt like a step in the wrong direction. However, by using a type of data structure referred to as a succinct data structure, we can store this tree in an almost optimal way. And one way of creating such a structure is by traversing the tree in depth-first fashion, setting a bit to 1 for every internal node that you pass through, or 0 for every leaf node. The resulting bit string will then uniquely represent the tree, and any node data that you have, such as the opacity values in our case, can then be tucked on at the end of this bit string, thus representing a micromap. So to summary, the way that I compressed micromaps are as follows. In a bottom-up fashion, combine any group of 4 subtriangles with the same opacity value to a single node, and then repeat this for all subdivision levels, forming our 4-way tree. And then repeat this for, and then encode that as a succinct bit stream, which you can see in this quick example. And for clarity, the tree and the opacity values, or data bits, are shown separately here, but of course that will be concatenated into a single stream. And even in this relatively small case, by comparing the bit string to the original and to the one we got here in the end, you can see that there's some potential for compression here. And if we were to look at the average result over all the scenes in this work, this turned out to be a very effective way at reducing the footprints of the micromaps, typically down to around 45 to 25% of the original size at reasonable subdivision levels. But in some extreme cases, such as for the new sponsor scene, we went all the way down to less than 1% of the original size, or expressed another way, compressed 110 times. However, we cannot just compress the micromaps. We also need some kind of way of looking up values from this new representation. And we can do that as follows, starting from the root node. After intersecting a triangle, represented by this dot on these slides, we need to figure out the index of the child that we need to visit, as well as update the barycentric coordinates to that particular subtriangle. And both of these things can readily be extracted with a single step of the indexing algorithm that I presented earlier. And this number then, this child index, becomes a kind of a counter. We need to step this number of bits into that bit string that represents the tree to find the next node that we should visit. However, if we are to encounter an internal node before this counter is 0, we need to also pass through all of the children owned by that node as well, as you can see here in the example labeled I on these slides. Or, in other words, we need to increment our counter by 4. Finally, when the counter is 0, we have found the node we want to investigate. And if the bit value of that, and the bit value in that tree string is 1, we need to repeat the above procedure, effectively going deeper down into the tree. And if the value is 0, we are done. And we are done, and the number of leaf nodes that we have passed until this point, that is, the number of zeros we passed through, is the index into the trailing bit string where we will find our opacity value. And with a method for looking up the values, we obviously need to compare this against some other ones. Thus, we have looked at the frame time performance, and in total investigated 6 different opacity algorithms. And they are micromaps themselves, but emulated in software using a small framework running in a any shader, the succinct tree encoding, or the succinctly tree encoded micromap that I just described, as well as Vulkan-based micromaps built using the fast build and the fast trace flag, very similar to how acceleration structures are built. And then we also compare this against using a kind of bit mask, where each bit in the mask represents a pixel in the original texture, as well as the original alpha texture, to see how all of them compare. And in all cases, we test out both the 2-state version and the 4-state mode of micromaps to see how they differ. And perhaps a little bit arbitrary maybe, we also lock the subdivision levels to a fixed value for each evaluation. And as you can see then, for 2-state micromaps, this will actually determine the final look of the scene, But if you at least use any hit shader that looks up the alpha texture, you will not really see a difference when using the four-state mode of micromaps, typically because it's just a performance knob in that case. As for the scenes we tested, micromaps are really only used in scenes with loads of alpha masks. So I chose the following scenes to try out all of these methods, which includes a decent sampling of old and modern content, as well as several orders of geometric complexity. And as I hope you can see from these images, I only really used a quite simple refining ambient occlusion rendering algorithm to keep things simple. This, however, also means that more complicated shading algorithms would likely benefit a lot more than what these results are showing. But that is out of the scope of this paper. And thankfully, we don't really have to look through reams of data to discern any particular pattern. Practically all plots have roughly the same shape, and we can roughly see the following. Using micromaps, software or hardware-based, is in general better than using either bit mask or textures, but not always by a large margin. And for software micromaps in particular, you can get a bit of a mixed bag of results. Sometimes you can lose as much as 30% of your frame time, but in other times you can gain as much as 16%. So it's really up to the user to make sure that they are applied properly. Whereas for a 4080, where you have hardware acceleration for micromaps, you will only ever lose, at least in these test cases, lose as much as 2% of your frame time, whereas you can gain as much as 29%. And unfortunately, the tree lookup algorithm that we invented only really performs okay for the first 3 or 4 subdivision levels. After that, it basically scales out of control, something that I will get back to in a bit. Interestingly, I was expecting the fast build and the fast trace to perform basically equivalently. However, there is a noticeable delta between them for some reason that you can see in the red and the orange lines. However, I don't know why that is. If someone from NVIDIA would like to speak up, I would be more than happy to hear it. And if we change things around a little bit into a somewhat easier scene, a single twig from the new sponsor scene. And here we can see a bit more of an interesting pattern. Although do note that I have removed the tree results in this particular plots in order to make things actually visible. And the most notable part here is that for a 3080, you will only ever benefit when you're using over using textures in a very small region, again, around the 9 subdivision levels. After that, you even increase performance again, you reduce the performance again. However, do note the axes on these plots. The ranges are relatively small, all things considered, and the scene itself is a bit unrealistic. Which then brings me back to the tree method itself. Why does it perform so poorly? With the data packed so much more densely, surely caching should really help it, or at least make it comparable to the other methods. And I believe the main issue is this. When we want to find one of the rightmost children in a tree, we end up having to scan through all of the intervening subtrees, as seen in these examples. This is fine when the tree is relatively small, but is not really acceptable when the tree gets bigger. On average, it almost quadruples the number of bits that needs to be scanned when you add another level to the tree. And this is obviously problematic for something that should be comparable to an instant lookup, similar to a texture fetch. So how we fix this in the future? A tree-based structure do seem like a good fit for compressing micromaps, but this initial lookup algorithm requires a bit of rework to be practical for larger maps, or at least to make it feasible to realize in hardware along with the rest of the ray tracing pipeline. Thankfully, there are numerous ways of restructuring tree, one of which is at least bound to be more practical. Also, there are currently only 2 types of micromaps out there, opacity micromaps and displacement micromaps. But there seems to be at least some ongoing work out there to create several other types of micromaps to store colors, normals, or similar data. So it would be interesting to see if such attribute micromaps could be compressed using similar techniques. Further, I only really considered lossless techniques in this work to make sure that everything matched the original micromap. But it could be interesting to see what happens if you allow everything to be lossy, to provide some kind of approximation for level of detail for faraway objects, or something similar. And interestingly, the indexing algorithm that I presented in the beginning is actually very generalizable. The same basic approach could really be used for a number of different shapes. So investing in that further could also lead to a number of interesting applications. But to wrap things up, as a part of this work, we have done the following. Provided an arguably more descriptive algorithm for mapping barycentric coordinates to micromap indices, and used said method to create a compression algorithm for micromaps based on succinct trees, which is capable of reducing the memory footprint by more than 110 times. We also evaluated the frame time performance of this method, quickly realizing that while the method works, or in its practical for small maps, it is not useful for larger ones in its current form. And finally, the result was compared against various other methods, as well as the official Vulkan opacity micromaps, which itself showed a performance uplift by up to 29%. And with that, I think it's time to conclude and open up for questions, and hopefully, of course, some answers.
Okay, we've got time for a couple of questions. Go ahead. Alex.
Is mip mapping possible with your approach?
Repeat the question.
Oh, the question is mip mapping practical or useful with this approach?
Yes.
I don't know. I think you could do some kind of mip mapping strategy with it, but I guess your question is more, is it useful for the tree? I think you could try to map some kind of MIP level to the various hierarchies of the trees and use that. But that is not something that I have looked into at the current date.
Thank you. Over here.
I will yell. For your succinct representation of your triangle, it's all linear representation. Have you tried Morton codes or some sort of Z-filling curve?
Oh, the question is, have I tried using Morton codes or something like that in order to traverse my tree? Is that your question?
For representation, yes.
I have not tried that. The thought didn't really occur to me, as the original micromap is actually some kind of C-curve order thing. But it could be something interesting to investigate as well.
Then Alex.
Just a comment on the selection of a single twig. Do you think that's a representative for a game when you only have basically all the arrays hit something that has none of bait?
I would say that is not, oh, sorry. Is the twig scene that I showed you before a representable example? I would say that that is not really the case. It's mostly used to see some kind of pattern and see how the actual hardware behaves under those circumstances.
Good. I think we have time for one more question, if any. Okay, I've got one for you. What are some cases where we use any hit shaders but where OMMs don't work well?
I actually prepared an example of just that. Perfect chef. This is a very good example, taken directly from the San Miguel scene. Basically, you're in one of the corridors behind the scenes with loads of trees using opacity micromaps. However, almost all of them are occluded, but when you're tracing your race, you're going to have to call the NH shader anyways. So this is a case where you can actually lose quite a bit of performance, but mostly only for software-based approaches or for the 3080 in this case. For hardware ones, you barely see the performance hit at all.
Got it. Thank you. Okay, let's thank Gustav and Michael one more time. Okay, thank you. Our next paper is, I don't know the name. The name's really long. It's about dense geometry format. Think of it like texture compression, but for geometry. And it's by Josh Barzak, Karsten Bentine, and myself from AMD. And Josh is our presenter. So take it away, Josh.
Good. Thank you, Dave. Thank you for the introduction. The name of the paper is DGF, a dense hardware-friendly format for lossily compressing meshes with arbitrary topologies, which is a very long title. Good afternoon, everyone. Thank you for being here, and I'm excited to present this work. So to set the stage, historically in graphics, what we've done, we've taken our triangle jet meshes, we've stored them in vertex and index buffers in some form, and we've put this in GPU memory, and we've passed it directly to a hardware rasterizer and produced pixels. A few years ago, we added ray tracing to this pipeline, so now we patch our meshes through driver routines which produce vendor-specific acceleration structures that the hardware can consume. In the same time frame, systems like Nanite have raised the bar for model complexity by using very compact triangle representations which are directly rasterized, in some cases directly in software from compute shaders. Formats like these can't be consumed directly by the API. It doesn't know about them, it doesn't know what they are. So instead, we need to decode them into something which can use the existing paths, which the API does understand. And this adds latency and memory pressure. Even if that restriction were removed, the acceleration structures as they exist today are much too large to support future content, which is being authored with these lower data rates in mind. So if we look at the contents of these acceleration structures, if we kind of break them open and look at what's in them, we find that a considerable amount of memory goes to the triangle representation. The vertices are stored generally in single precision floats, and they're structured so that the entire triangle can be pulled in using one memory read, which is very important for an efficient hardware intersection pipeline, but adds considerable redundancy. And if we can shrink that by a factor of 8, we can enable significant reductions in memory footprint for the acceleration structures and memory bandwidth for the traversal. So we propose to do that by doing for geometry shader data what formats like DXT, ETC, and ASTC have done in the past for texture data. We present a triangle representation that meets the needs of hardware by packing as many triangles as possible into a concise cache-aligned structure. By moving the compression step outside of the driver, we can transform the data in ways which are either too slow to do at runtime practically, or which would violate the API spec in some way. So in this new world with this usage model, instead of directly building an acceleration structure from uncompressed geometry, applications can preprocess their data offline, which produces sets of SAH-efficient blocks, which can then be sent to the driver. This should result in smaller acceleration structures and should also reduce build time because, 1, the input data is much smaller, 2, the data has been prearranged into SAH-efficient groups, which the BVH builder can take advantage of. For animated geometry, it's also possible to compress blocks conservatively so they can be updated at runtime with new vertex positions, similar to what's done today for BVH updates. Instead of a fixed encoding precision for the vertices, we opted for fine-grained control. Users can make precise trade-offs between accuracy and compression rate based on the needs of the content and the type of shading that's in use. Another advantage of the fine-grained control is that if compression artifacts become a problem, they can generally be fixed by dragging a slider and adding more precision and using a few more bits. We compress the input mesh while preserving the connectivity. This is another key design decision. We don't require any remeshing or resampling in order to use this compression. That's a labor-intensive process if it's done manually, and the automated algorithms, while they're there, they can be slow and difficult to control in practice, particularly for really large meshes. By preserving the topology, we're able to preserve sharp corners and important features like UV chart boundaries or LOD cluster boundaries, things of that sort. We use a fixed point coordinate system for DGF, similar to what's used in Nanite. For a set of triangles in a block, we store the lower left corner of the vertex bounding box as a 24-bit signed integer, which we call the anchor. For each of the vertices in a block, we store an unsigned offset from the anchor whose bit width is variable and can vary on a per block basis. To decode a vertex, we add the anchor and the offset together, convert the result to floating point, and multiply by a power 2 scale factor, which takes us from this fixed point space to a more conventional floating point object coordinate system. The scale factor stored in the block is an 8-bit IEEE exponent. It's tucked away in the header. We encode connectivity using a form of generalized triangle strip. So for each triangle, we have a 2-bit code that tells us how we're going to connect this triangle up to the previous ones. One option is just to restart the strip and consume 3 completely different vertices. We can also choose to consume 1 vertex and dangle the triangle off of one of the 2 edges of the predecessor, one or the other of them. Edges are reversed when they're reused to ensure that the winding is consistent. If you have a mesh with mixed winding or non-manifold cases, more than 2 triangles on an edge, these can be encoded by restarting in the appropriate places. Since we have 1 more bit pattern available to us, we also allow backtracking 1 position and reusing whichever edge we didn't use to get here in the first place. This option is useful for avoiding restarts if the strip generation happens to paint itself into a corner, which we'll talk about. Vertex reuse is very important, so we also store a compressed index buffer for the strip. After building a strip for this mesh, if we sort the vertices by first use, we end up with the index buffer to the right. And if I highlight the indices that we've seen before, we see that all of the first use entries, which are the white ones, are always going to be sequential. This means that instead of storing these, we can store 1 bit per index telling us whether or not it's the first one. And every time we see one of these, we can increment a counter to generate the index value. The non-first indices, the red ones, still need to be directly stored, but we have a lot less of them to deal with now. In order to form these strips efficiently, we need the ability in the encoder to reorder the input triangles and to rotate vertices in a winding preserving way. So applications, if they encode the DGF, need to post-process any sideband data that they have that depends on the input triangle order. This might be buffers with triangle colors, face normals, index buffers, things of that sort. This is a familiar process for developers. Post-transform cache optimization for rasterization has a very similar requirement, and it's widely used today. Because we're allowed to reorder the triangles, we can also save quite a bit of space by making the primitive ID implicit. We no longer have to store the input primitive index in the acceleration structure. Instead, we can store a 29-bit base for each block and offset it by the triangle's position in the block, which makes still gives us a consistent incrementing index space, but it uses much less storage. In order to fully support the APIs, we also need to store a 24-bit geom ID and 1-bit opacity for each of the triangles. These are often correlated, so we take them and glue them together into a 25-bit value, which we store in one of 2 ways. If all the triangles in the block happen to have the same value, which happens quite a lot, and if the value is small enough, we can store it directly in the block header and not use any additional space. Otherwise, we store an array of unique IDs in the block and a per triangle selector which picks one of them from that array. Geometry IDs tend to have a lot of local similarity. You tend to have a lot of triangles in the same place using the same materials or from the same source, so this is often very small. It compresses very well. The IDs in the block are further compressed by identifying high order bits that have the same value and only storing these once. Details of that are in the paper. So to encode DGF, we first partition the geometry into SAH-efficient clusters. We begin with 1 cluster for the whole model, and we repeatedly subdivide according to the surface area heuristic until the size of all the clusters that are left is below some user-specified threshold. This is the exact same process as your classical top-down SAH-based BVH construction, except that we don't need to store the tree. We just go build the leaf triangle arrangements for it. For all the results in the paper, we use a threshold of 128 triangles. The next step is to snap the vertices onto fixed point grid, which for floating point input is the only source of error for DGF. After this initial quantization, all of the remaining steps are lossless. The grid resolution is a power of 2, and it's based on that user-specified target bit width for the vertex coordinates. In our encoder, we use the same quantization grid for every block for the entire model, which prevents cracking. But that isn't necessarily a hard requirement. You do have the option of being smarter and varying it block per block if that's a useful thing. Earlier, I said that the per vertex offsets in the blocks can go up to 16 bits. However, we can actually quantize to as high as 24 bits of precision as long as the length of all of the cluster bounding boxes in that quantized space will fit into 16 bits. For large triangles, this might not be the case. If you have something really big or if your coordinates are too big, overflow can happen. And if that happens, we snap precision downwards in order to prevent overflow. Details of that are discussed in the paper. So after we have our set of quantized clusters, we use a greedy algorithm to arrange each cluster's triangles into one or more blocks. We do a Morton ordering of the triangles and pick the lowest one to start with. And at each step, we select a new triangle which shares the most vertices with those that are already in our candidate block. That continues until we can no longer form a block with the triangles that are left, and at that point, we start a new one and continue the process. We prioritize vertex reuse here because that seems to be the single biggest factor for efficient compression rates. Vertices are big, they're hard to compress efficiently, and minimizing the number of vertices and the amount of sharing within a block seems to give the best result. To build the triangle strips for a block, we prioritize the triangles that have a minimum number of neighboring triangles available which are not already in the strip. So we build a graph and we pull things out of the graph and add it to the strip greedily based on valence. So we pick an arbitrary minimum neighbor triangle, we add it to the strip, and then we pick one of its neighbors to add next and continue this process at each step choosing the loneliest neighbor triangle. Now that can cause us to get stuck in corners, and that is actually intentional because oftentimes, as shown here, we can backtrack and continue the strip. And this minimum neighbor heuristic will cause us to walk along the mesh boundaries and scoop up isolated triangles as we see them and then backtrack back into place. If we do happen to get stuck, we pick an arbitrary minimum neighbor triangle to restart from, and we continue the process until everything's gone into the strip. Before presenting results, I'm going to briefly describe related work that we compared to. Our first comparison is with Google Draco, which is a production codec that's aimed at reducing disk storage and network bandwidth for geometry data. It's a very compact codec. It uses quantized vertices, and its topology compression is based on Edgebreaker, which is a fairly seminal work in that field. Draco needs to be fully decompressed before rendering, so it's not suitable as a direct mesh representation, but it gives us a lower bound on encode speed and compression rate for our comparison. We also compared to a recent paper on compressed meshlets for rasterization. This format uses fixed width vertices, and its connectivity encoding is fairly similar to ours. It's also directly renderable from a mesh shader, but it's not a block-based codec. Accessing a given triangle might require multiple reads to pull indices and vertices in. We also compared to displaced micromeshes, which are meant to address some of the same problems that we do, but it's important to note that they are actually a fundamentally different thing in a lot of ways. So DMMs are a displacement mapping system, and they work by converting a dense mesh into a simpler base surface and then representing fine detail as displacement from the linear base surface. Right? It's a displacement mapping system, and for what it is, it's extremely good at what it does. It gets very impressive compression rates, and there's some very, very impressive ideas there around compressing the displacement data. DGF, in contrast, tries to be a general mesh representation. It takes the input that it's given and directly encodes it. And because of that, it just has to store more information, and it can't compete with a displacement map in terms of density. It's just not going to. DGF's advantage, the reason why we still feel it's relevant, is that it offers much more flexibility. It's a drop-in compressor which can encode any mesh without too much preconditioning and is usable in situations where displacement mapping may not be practical. Right, so our first graph shows compression density for various models. These are all fairly large models with I think the smallest is 6 million triangles, and it goes up from there. So the dark gray bar is the reference meshlet system, the mesh shader-based one. The light gray bar is DGF. We see that DGF edges this out because it performs more aggressive compression, but as expected, DMM, it gets a higher rate, and Draco gets a higher rate. Here we're looking at the effect of target precision on the compression rate for a range of models. What's unsurprising here is that the higher your target precision, the larger your size on average. But there's an interesting thing that you can see from the graph is that the spread also increases as the target bit width goes up. This has to do with differences in the meshes that are in the data set. Some meshes compress better than others. If you have a really dense mesh with vertices that are close together, the encoder can use smaller offsets for those vertices, even if the initial quantization precision was a lot higher. If you spread the vertices apart, you start needing more and more precision to represent, fully represent the maximum precision. But if you reduce your quantization factor, then those more highly spaced vertices start to need less space, and it starts to even out at the left side. Meshes that have a lot of access to the line geometry also benefit because we can turn down the bit rate on one of the axes if you're axis aligned most of the time, or if you're mostly axis aligned, you don't have to store as much. Here we're looking at compression time. We see that Draco's very good. I was actually impressed by how competitive it is. Even for these very large models with the tens of millions of triangles in them, the DGF compressor has a ways to go. There's considerable room for improvement here in terms of implementation quality and algorithm and even multi-threading, which we don't do in any of these results. The bulk of the running time for DGF is spent on the triangle strip generation, because this is done again and again and again during that block packing stage. When we're adding new triangles, we go and try and build a new strip, see if it fits, and repeat the process. So there's a very complex inner loop routine there that can be teased out. DMM doesn't fare very well because it does a lot of complex pre-processing to take this general input mesh and convert it into a form that a displacement map can handle. There's probably room for improvement there on implementation quality, but fundamentally the method needs to do more work to encode a general mesh, and this reflects that. Here are some traversal performance measurements. For this, we implemented 3 different experiments. The tallest column is an intersection shader, which does a conventional software right triangle intersection against a vertex and index buffer, and it uses a DXR intersection shader with 1 procedural leaf per triangle. The middle bar, the light gray DGF one, is doing the same thing, but its intersection tests against DGF blocks instead of the vertex index buffer. So considerably more computational overhead to do the decoding, but much lower bandwidth. We also compared to a DMM proxy, which intersects the base triangle for the DMM, but builds the BVH using the ABBs of the extruded prisms, which is representative in terms of memory bandwidth. Graph is showing the number of last level cast meshes, which is a strong predictor for performance in a hardware implementation, and as you can expect here, the smallest structure wins. DMM has a particular advantage in this case because it's building a BVH over a much smaller number of things. There's fewer base triangles in our input, and as a result, there's fewer internal nodes to traverse, and they get a benefit from that. So speaking of internal nodes, the last set of results is what happens if we take our DXR BVH, rip the triangle data out, and put DGF blocks in its place, but leaving the internal node structure the same. So we're looking at the relative size of the acceleration structure if we do that as compared to the DXR BVH in our target architecture. The left-hand column, the 2 triangles per leaf, is roughly what this target architecture does, and we see about a 50% reduction there. If we're willing to do more triangle tests at the leaf level, we can eliminate some more internal nodes and see a proportional larger benefit. It's also worth noting that architectures with smaller internal nodes will see a much larger proportional reduction, and this target architecture is actually the industry leader in internal node memory footprint at this time. Yep. So, in conclusion, we've presented a general purpose geometry compression system which has the potential to improve all aspects of ray tracing. It's relatively simple to integrate into a content pipeline. Several topics for future work. We need to study this in the context of rasterization. We need to take a closer look at BVH construction and validate that hypothesis that build time will get better. We think it will because N is going down by about a factor of 30 for that hierarchy construction step, but we need to prove that out. We also need to investigate animated content. How well does this fixed point quantized content hold up as you're moving things around and animating it? And lastly, where I think I see a big research opportunity, there's a lot of room for improvement in that initial encoding algorithm. There's probably a lot of things that you could try, and probably things that you all here thought of that I just didn't try yet. That's it. Thank you.
Okay, we've got a few minutes for questions because I was such a Nazi on the
Good job.
timekeeping. Yep. Okay, questions for Josh. Alex.
Any water tightness guarantees across blocks?
As long as you snap to the same, are there water tightness guarantees across blocks? As long as you've snapped the vertices consistently between the two, then everything should work out, which our encoder does. We use the same quantization space everywhere.
Go ahead.
Can you use DGF and DMM together? Theoretically, yes. I think there needs to be some architecture work done to marry those two things, but I'm actually very interested in the idea of using DGF for the base surface and then putting some kind of displacement on top. But that's a future topic. Do I have decoder performance compared to Draco? I don't have an apples-to-apples comparison on the CPU or anything like that, so no. Yeah.
I think I saw one more hand. Okay, yeah, go ahead, Alex.
So if I start pushing higher compression ratio, how do I know how much do I lose to the metrics you can give? Because it's lossy, right? So
yeah.
I don't know how much lossy I'm getting when I'm getting higher ratio.
Yeah, I mean, you'd have to derive something based on the size of, sorry.
The question was, how do you measure the amount of error as you drive up the compression bit rate?
Thanks, Dave. You'd have to, it's some function of the object size and the bit width, and you could probably measure what the minimum rounding error is going to be there. So if you wanted to expose it in terms of maximum world space distance, you could do it that way too. It's just different math.
Or you could just decompress it and compare the decompressed result to the pre-compressed.
Yeah.
Okay, I think that's it. Let's thank our speaker one more time.
Thank you.
Okay, our concluding talk in this session is real-time procedural generation with GPU work graphs. This was work done in collaboration between AMD and Coburg University. The authors are from those institutions and some from both. Our speaker is Bastian Kut, and the other authors are Max Oberberger, Carsten Faber, Dominic Baumeister, Matthias Kaitis, and Karen Meyer.
All right, test. Does this work? Here's the feedback. Okay, good. Hello and welcome. This presentation is about a real-time procedural generation system using the novel GPU Work Graphs API. And for the beginning, I have to give an introduction to GPU Work Graphs. And the idea is it's a novel API feature is that you have a compute kernel and you can create work items for another compute kernel from it. So for example, here we have a worker kernel and it gets work items from the work creator. And a work item is associated with some kind of parameters. For example, in this case, the job struct. And this would be a very simple work graph, but you can go more complicated. For example, the node B could then create work items for node C or for node D, which create work items for itself. So this was a very brief introduction. You will get a more thorough one after the break by Max. And let's get started with procedure generation. And I want to make a short list of existing procedure systems. So I have to include Houdini. Then there is Blender with its geometry nodes, and the most recent addition is Unreal Engine. They are currently developing their own PCG system. All right, let's take a look at how or rather where these softwares generated geometry. So for Houdini and Blender, if you want to use the generated geometry for real-time rendering, you basically generate it on the CPU for the most part. Then you have to store it to disk, to some polygon format. You basically bake it, and then you load it later for rendering. And what Unreal Engine achieves with their system is that the generation happens in engine, and you can basically skip this baking part to disk. And what we want to do today is we want to skip the CPU part and let the GPU generate everything that it also wants to render. So let's make a list of requirements, and let's add the first requirement. We want to be GPU only. Next up, if we take a look at this Unreal Engine PCG example, you can see that while we are dragging around this structure, the generation doesn't actually update. Only if we let go of the mouse button, it will take like a second or two for the generation to run, and then we can see the result. And this is kind of annoying because while you're dragging, you don't know how the final scene will look like. So let's add to our requirements. We want to have instant updates when editing. Next up, let's take a look how artists can control the generation. So here I want to demonstrate something that we call the parameters for the generation, the control parameters. And as you can see here, these three values influence the generation of this muffin. This could be more complicated. For example, here we have a bounding box, and this bounding box defines the shape of this bench. And if we manipulate this bounding box, it could also be, for example, for lying down, or we could manipulate how the height of the back support. And we can go more complicated than that. For example, a polygon could define the whole shape of a building or so. So we also want to have our system to have control parameters, so let's add it to our requirements. Next up, if we take a look at our of existing procedure generation systems, we can see that they all are based on node graphs. And what these node graphs do, they basically nodes receive control parameters and output control parameters, and then these nodes are reusable, and the user can plug them together, these nodes, to generate a complex scene. And this is also what we want to do. We want to have a hierarchy of reusable nodes. All right, so let's start with our first example. We want to generate this marketplace. And for this, we went on a research trip to the Coburg Christmas market and observed that the basic shape of this market can be described as a polygon again. And from the corners of this polygon, there are paths leading towards the center of the market. And in between these paths, there are more interconnecting paths. And in between these paths, there's something we call booth islands, or there are the booths. And so there we would like to place some fitting assets, for example, tents or market stalls or whatnot. And in the center of the market, there's a special area with a special asset, for example, a well or a tree or a statue. And what this layout looks like is very similar to something that's called the straight skeleton of a polygon. By Eichholzer, and if we take a look how it works is, so you have the initial polygon and then you shrink it. And while shrinking, you have to handle events. So for example, in this case, we shrunk a little bit and now 2 points of the polygon merged into one. So that's the merge event. And the other event that can occur is the so-called split event, where the polygon will split into two. And for our market generation, we also have to handle these kind of events. So let's see how we do that. So this is our example polygon where we want to generate a marketplace into. And we have a market node of a work graph, and it receives this polygon as input. And this is how it would look like in code. So we have the market node, kernel, and it receives an input record, and this input record is a struct containing the points of the polygon. And this syntax means that when this market is launched, we receive one thread group. And because the thread group has 32 threads, we get one wave, basically. And what we do with the threads of this wave, we assign one thread to one corner of the polygon and compute when the next event will happen for that point. And then we have to find out what's the closest event, so we can just use a wave intrinsic. So for example, in this case, it would be thread 2 or corner 2. And then we can find out, okay, we can actually shrink the polygon before handling anything. Okay, what we do now, we can write some records for a node called path. So it should generate the paths for this first ring. And then we can make some space for these paths. And we can write records for the booths islands. So let's take a look at how this would look like in code. So here we add some more outputs to our node for the path and the Booth Island nodes. Okay, so let's take a look at how the Booth Island generates geometry, or how our whole system generates geometry. So here we would like to fill this quad control structure with market booths. And one way to do this is to write to a draw list, and then later just use execute interact and draw this draw list. And for this you would need some kind of, because everything runs in parallel, you would need like some kind of interlocked add and reserve a slot in the draw list. You could go a little more modern. You could write to a BVH instance list and then later build a TLS from that list, but would be very similar. Or the more modern approach, or more recent addition to work graphs are graphic leaf nodes, where you can directly draw from the work graphs to using a mesh shader. All right, so these are our three options. Okay, so we have now generated our first string, and now we are at a similar position as we were when we started generating. We have a polygon, we want to generate a market into it, so let's recurse. And this is how it would look like in code. So we add another output to our market node, which is to the market, and we have to additionally declare how deep this recursion can go in the worst case. Okay, and now we can again write records for the Booth Island and for the path. And now we can no longer shrink the polygon because the first event happens, in this case, the split event. And what we do now, we said we have to split the polygon into two, so let's recurse again, but this time into two. And for the right half, it's really small. There's no more space for another ring of Booth Islands, so let's create a market center, in this case, a well. And for the other half, we still have space. We can add another ring, write our outputs, and conclude with a market center, in this case, a tree. And this concludes our market generation. If you take a look at the straight skeleton again, we can see it's very similar. In our actual implementation, we add a little bit of noise after each iteration to the points of the polygon, so it looks more natural. All right, so let's see it in action. Here we can see the rings generating. It's for the visualization, it actually runs in like 1 millisecond. And here you can see us dragging around a point of the polygon, and you can see the generation updating instantly to what we are doing. All right, so this fulfills our requirements so far, but there's more to it, because if you take a look here, there's something that I haven't mentioned so far. We actually generate garlands in between Booth Islands who have been generated independent from each other. So let's talk about how we achieve that. And that's a feature that is similar in other systems. So we have this clip from Unreal Engine again, and here we can see in the red box that when this white structure intersects with something, Unreal Engine will generate this connecting stem. And for the blue box, it doesn't find any connecting, like any existing geometry, so it doesn't create anything. And this is something we call dependent generation, so the generating reacting to something that's already there, or reacting to other procedural geometry. So let's get back to our garland example and talk about how we achieve it. So here we have the connecting points for our garland, and we now have to find them when running the generation. So we need some kind of spatial GPU data structure that is fast to create and update and to access. So we thought for a little bit. Wait, we already have that, a ray tracing BVH. And so creating it is just a matter of issuing API calls, right? And we already established that we can write to a BVH instance list, so just let's do that. And here's how we do it in a more specific way. So for these garlands, we create something which we call markers, and these markers are invisible when ray tracing for lighting effects, for example, and we use BVH instance flags for that, and we only activate the flag for the markers when we want to generate the garlands. And what we do is we shoot rays into the vicinity of these garland points, so something like this, and then we can generate the garland. All right, we can do more with this dependent generation idea with ray tracing. For example, we can generate ivy on existing geometry. So let's talk about how we do that. So we have an ivy branch node, and it receives a transformation as input. And what we want now, we want this ivy branch node to generate ivy onto an existing surface. And here's the loop that ivy branch runs. So first, ivy branch shoots rays into the growth direction approximately. Then, based on the result, the transformation is updated. Then we draw assets, for example, you get the branch and the leaves, and then there's a random chance that this branch can split into two. And for that, we again use recursion. So let's see how this would look like. So the ivy grows onto the surface and then terminates at some point. And here's how this looks like in action. So here we drag around this transformation, and you can see when there's nothing to grow, and it will just grow downwards. And when it finds the surface, it will grow along the surface. This is cool. This is still kind of boring. So let's add a parent to ivy branch, something we call the ivy area. And ivy area receives a bounding box as a control parameter and outputs a bunch of transformations for ivy branch. So here we want to fill a whole roof with ivy. And you can see us dragging around the bounding box and now adjusting its scale. And what you will see in a minute or in a second, that this house is also procedure generated, so we can also change its control parameter, and the ivy is also adjusting to it immediately. All right, one last thing we did with the dependent generation, we generate ground clutter everywhere, and you see it here. We use ray tracing to find like how bright a spot is. And based on the brightness, we place either mushrooms or grass, for example. And there's also something here that I haven't mentioned so far. We can actually we can say that we only have to generate the geometry for the current frame, right? The generation runs within a frame, so we can only or have a new possibility for optimization. We only have to generate the geometry that influencing the current frame. So in this case, we only create the ground clutter that's inside the frustum. So let's add that to our requirements. We want to have cult generation. All right, so let's talk about performance. So here we have our test scene. And on the left side, we can see an overview where we cannot cull any generation. We have to generate everything. On the right side, we have a little smaller scene, so we have to generate less. And here are our timings. So you can see our generation runs in this time. And for the little smaller scene with the market, we are a little faster. And you can also see here, we also generated a little less because everything else was culled. But there's also pretty terrible render timings, right? Like almost 30 milliseconds is absolutely acceptable. And well, what's the reason for this? It's the number of draw calls. Right now, we submit one draw call per generated object and don't use any instancing or whatnot. So we have to do this we have to fix this. So let's add instance rendering as the last requirement for a system. Let's talk about how we achieve that. In work graphs, there's a special feature or special launch mode for nodes, which is called coalescing. And what this does is here we receive up to 256 draw asset records, and then can output up to 256 asset records. But in the best case, we can combine some draw calls using instancing. So in this example, what we would do, we sort this list, and then we can see, okay, we have to submit one draw call for the branches, one for the market tents, and so on. Let's take a look at how much this improved it. And as you can see here, the number of draw calls significantly was reduced, and so did the render timings. So we have achieved what we wanted. And also the generation times went down a little bit. All right, so this concludes our requirements list. That's the only thing that's left to say is source code is and will be available on GPU Open. Most parts of it. We've already published some parts of it, so take a look. All right, so in conclusion, work graphs plus ray tracing plus mesh shaders, cool scene. So thank you for your attention, and I'm open for questions.
Go ahead, Alex.
It is amazing, but why do you need to generate content that fast? I mean, it is like
Yeah, so one reason, I mean, I mentioned you can do it cold, so you only can like... Oh, sorry, okay, he asked why I have to generate that quickly. So like, what's the point of it? So first, you can do cult generation. You can only generate the stuff that's currently required for the current frame, right? So you don't have to worry about culling because you only generate the stuff that's visible, right? Another reason would be real-time editing, right? I showed you where I edited the mark place. It's really annoying, like if you would like drag it around, don't see what's happening, then let go get the coffee, and then come back and then see what the result is. You would want it to see immediately what's happening, right? Or an artist would want that. And of course, well, it's resource efficient and stuff, right? So these are the reasons. Okay, maybe, yeah.
If I understand correctly, your straight skeleton implementation, you can shrink by the width of your market, with a market island node. Can that be extended just, or maybe is it implemented this way already, to calculate the generic straight skeleton of any simple polygon with a GPU implementation?
Yeah, so, sorry, okay. He's asking whether I can use this implementation of the straight skeleton for any straight skeleton, right? So this specific implementation is optimized for polygons of 32 points or less, so one wave. But I'm confident that there could be something in there. So if you are willing to like make an implementation for it and maybe a paper, sure, go ahead. Yeah.
Follow up on the fast, at least on your examples, grid size is always 1 by 1 forecasted node, which means you're using one work group on the entire GPU, the rest doing nothing. Is that the best you can do, or this is just an example?
Yeah, so for the marked, okay, he's asking. So I in my examples, I always had the grid size of 1, 1, 1, which is kind of counterintuitively or kind of bad for GPU programming, right? For the market, I mean, I guess you would agree that there's not really a point in generating 1,000 markets at the same time, right? There's not really a use case for that. And I also wrote in the paper that most of our generation, like the market alone doesn't occupy a GPU, right? But if you like, for example, the Ivy generation, also the first iteration of Ivy will not occupy the GPU, but if you combine all these generation things and let the Ivy split and recurse and have this exponential growth, then it will at some point occupy a GPU. Okay?
So I'm wondering, you say that you're doing culling to the view system, but it still means that you're doing a lot of work every frame to generate the exact same assets if the view hasn't changed very much. So you thought about how you can expand the system to take advantage of frame-to-frame coherence.
Yeah, so what we could do right now is, right, okay. So he's asking whether we could use, like right now we are generating everything every frame, and it's kind of wasteful. And yeah, what we can do, I mean, the most basic thing we can do, we just click not generate, like we could just stop running the work graph and then use the draw list to just draw everything, right? That's the easiest thing.
Sure, but you're going to have to combine that with, as your view changes, you're doing culling, you're going to have to generate the places that have been really revealed, right?
I didn't get that.
If you're doing the culling to your view cluster, you generate once, but then when you move your view
yeah.
you've got to fill in the distributed areas.
That's true, but so he's saying like when I move the camera, I could like reuse some of the generation, right? Yes, I mean generation was so fast that we didn't even think about that. So yeah, you're right. no idea. Yeah, probably.
Another thought here, and you can tell me whether you think this is up in the night or not, is in the context of the other two papers here about content compression for GPU rendering, you can think of the decompression as similar to the effort to generate this content, right? And you do that every frame without complaining about it. So you can think of this generation in that same way.
Totally, yeah.
Aaron.
This is really, really cool, but somewhat relatively low poly content. Would the performance characteristics of either the work graphs or rendering change a lot if suddenly this were 2 orders of magnitude, 3 orders of magnitude bigger?
So he's mentioning that the scenes you can see here is very low poly, and he's asking whether high poly stuff would be way more, like if every of the performance characteristics would change. So, I mean, for the most part, we generate an instance list, and it doesn't matter if this instance has 1,000,000 polygons or 100, right? It only matters for rendering, but we don't really optimize rendering here, right? That's not our worry. But as you've seen, like we also generate, for example, the ground clutter, right? And that ground clutter has like 50 million triangles or so, you can see here, yeah? So no, it doesn't really matter, yeah.
Go ahead.
CPU from the whole pipeline, right? Everything's generated on GPU. How does it work with the interactive scenarios like computer games, for example? How do you inform about collisions and all the interactions that happen?
Yeah, so he's asking, like, because I'm generating everything on the GPU, you cannot have the classic, like, CPU knows about, for example, collision, and then handle, like, for example, a character walking up to a market booth, and I don't know, because everything runs on a GPU. I mean, the tacky answer is to say, well, then let this stuff also happen on a GPU, like handle collision and stuff also on a GPU, right? And with work graphs, I think we're one step closer to let that be a reality. So, yeah.
Okay, great. Let's thank Bastian one more time. Okay, we're at the end of the session. We have a break until 3:15. That's 33 minutes, and then we'll be back here for the next Hot 3D session led by Wanzhang.
guys riding on backbiting and get away with lies. No matter what it takes, who is gonna cry? The only thing that matters is you get what you decide. But I know for sure the day will come when you first realize what you have done and you finally get your debt repaid and your vengeance served on a cold plate. You hear the roar of this shutdown when the world will stop without a sound. And the moment you will cry for help, that we only think about ourselves. Oh yeah. The first time that I met you, I thought you looked so sweet. I stood around for the hills, beating a retreat. And when I heard you talking with that alluring sound, should have recalled the sirens and how that things went down. Living on the trenches, looking for a way to escape. You always cut me down like a dreamers with them grapes. But never mind how I tried to leave you behind. I kept falling in your net. Oh, I've been so blind. But I know for sure the day will come when you first realize what have you done, and you finally get your debt repaid and revenge is served on a cold plate. And you hear the roar of the shutdown when the world will stop without a sound. And the moment you will cry for help, and we only think about ourselves. Oh yeah. About ourselves. About ourselves. But I know for sure that day will come when you first realize what you have done, and you finally get your debt repaid and revenge is served on a cold plate. Oh yeah, on a cold plate, on a cold plate, on a cold plate.
Okay, so welcome back to the second Hot 3D session. So maybe we also have two remarkable speakers came from the industry, AMD and NVIDIA. So maybe first the speaker, Max Overberg, came from AMD, dealing with so work graph and the mesh shader, yeah, something like that. So today he's gonna cover some kind of the work graph, broadly speaking, about the tutorial or some how to map on real hardware or something like that. So how to, you can learn definitely about that. Okay, thank you.
Yeah. All right, thanks for the introduction. Yeah, as said, I'm gonna talk a little bit about work graphs, how you can use it. So first part, and then the second part, we're actually gonna take a look, a sneak peek sort of under the hood and see how work graphs actually works on our AMD GPUs. But first, let's start with a little bit of context. There has been some general buzz around work graphs ever since the initial preview phase a bit more than a year ago, and early this year, on March 11th, the first 1.0 release came to the DirectX 12 specification. At GDC itself, we showed a small extension to work graphs, which brings the sort of long-lived dream of many graphics programmers that they can now issue draw calls directly from the GPU to reality. And earlier this month, we sort of brought this dream to everyone with the mesh nodes preview, which you can try right now. And AMD has been supporting all of these releases with a driver right from the get-go. And today, we've just seen a first talk on content you can do with work graphs. There's a poster back there with work graphs, and you've seen it come up in multiple talks already. So what is all this buzz about? Well, today, if you want to program a GPU, you're probably going to use one of these graphics APIs or something very similar. And these APIs are very nice. They give us access to quite a lot of features that just show how powerful GPUs have gotten in recent years. So we have, for example, different ways of rasterizing a scene, all the way to hardware-accelerated machine learning. But all of these graphics APIs have sort of one limiting factor in common, is that whenever we want to do something from the GPU, on the GPU, we have to explicitly tell it from the CPU to do something. So while the GPU itself have become quite powerful, they can't really decide themselves on what they want to do, at least not yet. You might say there is execute indirect, and you could create new work with that for the GPU. And yes, that's at least partially right. You can create work with execute indirect on a GPU and then execute it on a GPU, but you still need to explicitly tell the GPU to do so from the CPU. For example, you have to set your pipeline state, and then you have to tell the GPU, hey, this is where you just created some work, go execute that one. And if you try to do anything complex with it, you'll also have to deal with like a forest of barriers. And even more additionally, if you want to sort of have some data to go along with the work you've created, you also have to write a memory manage of some sort for that. So what are work graphs and how can they help us solve this problem? Well, work graphs are producer-consumer networks of work items flowing through a graph of nodes, all happening entirely on the GPU without any sort of intervention from the CPU. Now, there is a lot of information in that one sentence, so let's try to sort of unroll it piece by piece and maybe start with the last part, the nodes. Because typically when we programmed the GPU, we were using shaders. So what are these nodes now? And to sort of get to the bottom of that, we're going to take a look at one example shader. In this case, we sort of have some material shading. So we have a simple compute shader with 8 by 8 threads. And we can dispatch multiple of these thread groups to process an entire full screen texture. And as we're doing material shading, we can load some sort of material ID from another texture that has been outputted before by, for example, a rasterizer, compute rasterizer. And then we can use this material ID to decide on how we want to shade that particular pixel. Now, this approach is often referred to as an Uber shader and has quite a lot of downsides. For one, this shade material shader kernel has the worst case resource allocations of any of the material shaders, the worst case registers, and for example, if you're using shared memory or something. In addition, the switch case statement, GPUs don't really like that. There are a lot of divergent code flows in that. So we're looking for something better. And over the course of this talk, we're going to see how workers can actually help us to transform sort of this material shading example into a GPU-driven material shading that's quite friendly to GPU. So first step is we create a node, and that's very easy. You just write my shader is now a node. And then the next thing you have to figure out is, okay, how do I want to launch this node? And this is the first sort of major differentiator with work graphs from sort of regular compute shaders, execute indirect, or other sort of GPU graph-based implementations, that work graphs does not think in sort of dispatches or launches. Work graphs thinks in work items that are sort of processed by a shader kernel, or a node in this case. And there are different ways of how we can launch a node for a particular work item. The first and foremost is the broadcasting launch. This is quite similar to just dispatching a compute shader, and something you're probably quite familiar with already. And here we just say, okay, each work item gets a dispatch grid of thread groups. The second node launch is the thread launch. The closest resemblance to this would probably be dispatch rays in the DXR ray tracing specification, as this also allows us to have like thread granularity when launching work. And thread launches are also very similar to that one, because each thread in this thread launch node cannot see all the other threads. And sort of one advantage if we're using work graphs is work graphs isn't just going to launch one wave with just one thread working, but the scheduler can combine multiples of these work items and try to fill the entire GPU. And the last node launch, which you heard something before already, is the coalescing node launch. Now, at the surface, this might seem quite similar to the thread node launch in that we have multiple work items going to a single thread group. But in this case, we can actually set how many work items we want to receive and how large this thread group is going to be. And in this case, all the threads can also work together on processing these items. And you've just seen how you can, for example, use to turn a soup of draw calls into instance draw calls. So back to our material shading shader. In this case, we're sort of porting over a compute dispatch, so we're using a broadcasting launch. And the next thing is we're going to need to figure out how many thread groups we actually need to launch. And there are two ways to do that. The first one is we just write a static dispatch grid to each node. So every time you invoke this node, this many thread groups will be launched. Or the second way is you just write a maximum limit for that, and then have the actual number of thread groups set dynamically by a record. Now, what is a record? Well, a record is just a struct holding data, and a record is, well, the actual work item that's flowing through the graph. The term record and work item are sort of interchangeably used throughout work graphs. So in this case, we just have our three-dimensional dispatch grid telling us how many thread groups we want to launch. It's annotated by a special semantic. And if we want to use this with our node, we can just write it as an input to our function signature. And with this, we successfully created our first work graph node. The problem is we just have one node now. It's not really a graph. And we haven't solved any of the problems with a material shader. So we can sort of rinse and repeat and create a second node. In this case, we just call it shade pixel. And this one will just shade a single pixel. And as it's shading a single pixel, we can use the new thread launch mode, create a record for it, in where we define, okay, which pixel do we want this particular thread to shade. We can sort of then load this pixel information in our node. And for now, let's just copy over the material shading we had before. We'll get to how we can optimize that. If we then want to launch this second node, we can't just call this function. We have to declare it as sort of an output of our first node that we created. And this has sort of some special syntax attached to it. And you can see that if to connect the two nodes, we just use the same name as we used to declare the function name for the second node. And we also need to declare how many records we intend to output from our node. In this case, we have 8 by 8 threads. And each thread wants to write one of those records, so we have 8 by 8 threads at most. To then write some of these threads, there are some new intrinsics functions where you can sort of request output memory for one record from a system. You can then sort of write your data to it. In this case, it's the pixel coordinates, and then you send it off. And this is sort of very semblance of some message passing APIs in that you're never going to see anything from that record again. It's just gone. It's going to the systems. At some point, the scheduler will launch that node, but you'll never get any feedback from it. So the work graph only moves forwards, and there is no sort of feedback going backwards. And with this, we created a work graph. We now have 2 nodes in our graph. One is the producer, one is the consumer node. And of course, work graphs isn't just limited to 2 nodes. As you see in Bastian's talk, we can have many of them. But there are some limitations. For example, one of them is that we cannot have at most a graph depth of 32 nodes. And there are also some limits to the outputs. You've just seen sort of the output declaration we had. At most, each node can output 256 different records, which means we can in theory also output to 256 different nodes. And total across all of these outputs, we can at most sort of write 32 kilobytes of node or record memory. And of course, this just doesn't have to be sort of a tree-like structure. There can also be multiple nodes targeting the same node. As you've seen in Bastian's talk, recursion is also allowed, but only self-recursion. So you can't recurse between 2 nodes, and each of those recursion steps will count towards the 32-node graph depth limit. So with these limits sort of out of the way, let's get back to our material shading example and see how we can sort of optimize any of the problems. Because before we just copied over all this bad switch case, worst case resources code to the second node, and we now want to have an optimized implementation. To optimize this, what we really would want to do is we just have one of those thread launch kernels for each of the different materials. Then we can just write the specific code we want to run for each material in there, and have like a bunch of different nodes. And the problem is, okay, does this now win in our producer? We have like a stack of different outputs and run into this 256 output limit very quickly. The answer to that question is no. Work graphs actually specifically accounts for this use case with a special feature called node arrays. Node arrays allows you to bundle multiple nodes of the same launch type and the same sort of record together. So now we can address them sort of like a single node, but we can still decide which of the which sort of node in this node array to launch. And we'll see that when we look at our producer node. There are some small syntax changes. We have to say that we're now outputting to a node array. For some sort of allocation reason, we also have to say specify the size. But for example, unbounded sizes or sparse node arrays are also supported. And the second small change is when we sort of requested one of these records to write to, we now have to specify the material ID or the index into this node array that we want to write to. In this case, it's our material ID. And you can see that each thread can potentially write to a different node in the array. So essentially what we've done here is we've taken sort of this very bad, very unoptimized code for shading materials and turned it into a nicely GPU-driven material shading with the help of work graphs. And you can see some sort of example how our input to this might look like. Each different color represents a different material ID, and that will sort of get classified into different into the different nodes in our node array. And if you want to learn more about this, you can actually find the sample over on gpopen.com. So with this sort of small introduction on what work graphs are out of the way, you might ask yourself, okay, how does this actually work? So what has changed in GPUs that they now suddenly can start to decide what they want to launch, when they want to launch, and how they want to launch it? And to understand this, we're going to take a look at how work graphs work on the RDNA3 architecture. And first of all, we have to understand how we can launch any work on a GPU. So we're going to take a look at how a compute shader dispatch actually works in hardware. So when we want to launch a compute shader, we sort of write a dispatch command to a command list or record it to a command list. This is very similar for DirectX 12 and Vulkan. And if you're using, for example, OpenGL, that's all hidden by the driver. Once we finished writing all the commands to the command list, we can then submit this command list to one command queue. And this sort of sends it off to the driver and says, okay, please execute this work for me. And we're going to see what happens next. Next, the GPU driver sort of takes this command list that we've given it and copies it over to GPU memory. Obviously, it sort of changes the encoding such that the GPU can actually read it. And then we also need to send the GPU some sort of command of, hey, I've put this command list here in memory, go execute it. And the GPU driver sends this to the GPU through a ring buffer. And if you sort of take a look at what's happening then on the GPU, this ring buffer is connected to a so-called command processor, or more specifically the microengine scheduler, which is part of the command processor. And as you can sort of guess by the name, the microengine scheduler is responsible for scheduling these incoming commands from the CPU and sort of distributing them or executing them on the GPU. And to sort of actually execute some work, the microengine scheduler has access to a lot of different pipes or queues, however you might want to call them, which can then actually execute the work. And those are sort of sorted into graphics queues, which can then, so for example, draw stuff, and compute queues, which only can compute things. And you might actually recognize this sort of split between graphics and compute, as this is sort of also exposed in DirectX 12 and Vulkan. Now, in our example, let's say we just have submitted our command list to a compute queue. So the microengine scheduler grabs a sort of compute queue that doesn't have any work currently to do, and forwards it this command to execute this command list through another ring buffer. Now this compute queue here is sort of a small processor on the GPU that can be programmed by firmware. And in this case, the firmware is written to then read this command list from memory and sort of start executing the commands one by one. And this is where we find our dispatch that we sort of wrote to the command list from before. And the compute queue then can then sort of invoke waves and sort of start processing this dispatch. So we've seen that we can sort of write some command lists, some work to do from the CPU onto GPU memory, and then magically have the GPU execute that. So why can't we just do the same from the GPU itself? It's GPU memory, and that's exactly sort of what's happening with work graphs. With work graphs, we want to sort of continually write and read from these lists. So we can't just have the one long list. Instead, we can sort of use a ring buffer. And as we have multiple different nodes in our graphs, we can have one of those ring buffers for each of the different nodes. So in this case, we have an example graph with node A, B, C, and D. Node A can feed into node B and C, and node B and C itself themselves can feed into node D. We can then sort of modify the firmware on the compute queue to then sort of continuously scan these ring buffers for new work items, and then sort of decide on when to launch them and also how to launch them using the different launch modes. And this is, for example, how we can combine multiple of these work items, for example, for thread launch modes. So this all seems a bit easy. So let's just walk through one example and see how this goes. In this case, let's just say we have one record available for node A, which calls for 2 thread groups. So very easy, the compute queue can pick them up, launch 2 thread groups, in this case, which say, okay, each thread group occupies a single SIMD. Obviously, in reality, each SIMD could hold many more thread groups, but this is sort of a simplified example. Each of those thread groups can then themselves generate output for the nodes B and C. And we can then sort of use some atomics to increment the sort of counter in the ring buffer, and then just write those records to those ring buffers. And we can do the same thing for the second thread group, and now sort of all the records have been written to the ring buffers. We have finished working on node A, and the compute queue can once again sort of scan through all the ring buffers, see, okay, there's some work available for node C and D, let's just go ahead and launch that. And of course, we have sort of the same game repeating again. Each of those thread groups will generate some work items for node D, which you can see here. And we can again start writing them to the ring buffer for node D one at a time. Until something bad happened, because now we sort of run out of memory in the ring buffer for node D. And to make matters worse, we also ran out of space in the GPU to start sort of carving away at the work in node D in order to free space in a ring buffer. So maybe work graphs isn't that easy after all. So we obviously must have missed something, because this sort of deadlock scenario can't happen with a work graph. let's go back a few steps on when we decided to launch sort of the work items for node B and C. And see, with work graphs, you have to guarantee that every work item which goes into the graph can completely finish processing until sort of the leaf node, which would in this case be node D. And we call this for progress guarantees. And we need to find a way to ensure that these deadlocks can't happen again. And if we look at, for example, the first work item in the ring buffer for node B, we know from the output declarations of node B that it can at most write 2 records for node D. So if we want to prevent this sort of overfilling of ring buffer for node D, we can just make a small reservation and say, okay, whenever we launch a thread group for node B, we just have to keep in mind that it might write 2 records to node D, so we need to check that the space is available at all times. We can do the same thing for all the other work items in node B, ring buffer for node B, until we completely finish launching them. And now we see that the ring buffer for node D is sort of completely filled up with reservations. And that's exactly how we mitigate sort of the deadlock we had before. Because now we can't sort of add any more reservations to the ring buffer for node D, meaning we can't actually start launching the work for node C until sort of node D has finished processing. Or we know the actual output counts that node B will write to the ring buffer. In this case, sort of the overall occupancy of the GPU is now limited by the size of the ring buffer of node D. Of course, in this small example, the ring buffers are very small. In reality, the work graph runtime would size them in order to always be able to fill the entire GPU. Now, we've seen how sort of the normal compute nodes can be programmed, can flow through the graph, and how we can sort of mitigate bad things happening when executing them. And I mentioned before that many graphics programmers have this long-lived dream of being able to also draw directly from the GPU, or actually draw codes directly on the GPU. And this is what the mesh nodes feature enables for work graphs. It's sort of a new recent addition, and as of sort of, I think, 1.5 weeks ago, it's in public preview, so you can also try it if you have a compatible GPU. So let's see how we can sort of make that work as well. Well, a mesh node essentially adds a new node launch mode called mesh, and that's very similar to just launching a normal mesh shader. These nodes always have to be leaf nodes, and the mesh node launch could be sort of related or is very similar to the broadcasting node, in that it sort of also launches a grid of thread nodes, thread groups. And the nice thing with this is you can have different mesh shaders with sort of different PSOs. So there has to be some sort of PSO switching in there as well. So let's take a look at how that works. Here we have a sort of very similar graph, or simple graph. We have just one sort of normal compute node and one mesh node. The compute node is launching the mesh node. We've seen before that for the compute nodes, we sort of have this compute queue, which is continuing monitoring the ring buffer and launching them. But for the mesh nodes, those have to be launched by the graphics queues, because there's graphics state involved. You have to do the PSO switching. You have to sort of set up all the other things that's required for drawing. The nice thing here is that these graphics queues are also sort of programmable by firmware, so we can sort of apply the same tricks that we used for the compute nodes here. But this would mean now that we have sort of a graphics and compute queue working at the same time, and for them to sort of get along nicely, the microengine scheduler can launch them in what's called a gang submit, which sort of joins the two together and says, okay, you now work together on this work graph. And they sort of can split the work between them, where the compute node queue still sort of checks all the compute nodes, launches them, and the graphics node sort of, the graphics queue only checks for the mesh nodes. So we can have sort of graphics or mesh node records going into the graphics queue, and can have mesh shaders launched on the GPU. So this sort of completes draw codes directly from the GPU. And obviously, each of those mesh shaders also can output triangles to the rasterizer. Those have to be processed by a pixel shader at some point. The sort of whole mechanism for launching pixel shaders is still running sort of in the background. That's completely detached from any of those two queues that I mentioned. And we still have the compute queue active, so the GPU can sort of continue decide on trying to fill itself with as much work as possible and running sort of compute work and graphics work side by side without any sort of barriers or other things that you explicitly need to add in order to make this sort of magic work. And you've seen this in Bastian's talk and sort of how this can be used to procedurally generate the entire world. So to summarize, we've seen that work graphs are GPU-driven producer-consumer networks. There is GPU-managed memory for the records, and there is sort of special features happening so that you can never run out of this GPU-managed memory. If you want to learn more about work graphs, we have some blog posts, samples, and obviously the paper you've just seen available over on gpuopen.com, so be sure to check that out. And this is sort of where you come in. We want to hear from you. What do you sort of, or what are your ideas for work graphs? You've seen sort of a glimpse at the specification now, what you can do with work graphs already. Are there any features we're missing? Do you have any sort of feedback, suggestions? Either come up to me or Bastian. We're still here at the conference for the next days. We'll also be at SIGGRAPH. So if you see us, just come up to us, talk to us, or just write me an email with sort of, yeah, we want to hear what you want to do with work graphs, or if you have any ideas on sort of how we can still keep evolving work graphs, because as you've seen, it's still a sort of very active and alive standard that's continually evolving. Yeah. There is some reading homework, and I think with that, we'll have some time for questions.
Questions for Max?
So, two questions in one. What are the current plans for interoperability with both ray tracing and DirectML in the future?
So ray tracing, you can just use ray queries directly inside work graphs. And then, for example, for your ray tracing, you could connect up the material shading I showed before to whatever you hit. So if you just trace a ray, you hit some material, you can sort of use that to do material shading. As for sort of the whole DXR 1.0 stack with the sort of different shaders, yeah, that might come to work graphs, might not. It's kind of hard to integrate those two together. Same probably goes for DirectML.
Other questions?
Yeah. Would you want to shout?
Yeah.
Or?
You said that you're sizing the buffer so you can always fill the GPU entirely. For like the demo of the previous talk, like how much VRAM is there?
Okay, question was, I said before that we're sizing those ring buffers in order to fill the entire GPU. And the question was for the demo that Bastian showed, what would be some actual numbers? If I remember correctly, it was 196 megabytes of sort of backing, it's called backing memory for work graphs. The nice thing of this is it's actually constant. I have some slides if you're interested. This is sort of a different example. This is a computer rasterizer sample you can find on gpuopen.com. Similar problem, you're not classifying by material, you're classifying by triangle size. So however many pixels those take up. And for example, if you only want to rasterize a small number of triangles, in this case, I think the original sponsor scene is at 81,000 triangles, you can see that work graphs, the backing memory requirement for those is sort of exceeds the one you would need for execute indirect. But sort of computer graphics has come a long way. So if you switch to a more detailed scene, you can see that the work graph's backend memory is actually independent of the workload size. In this case, you can see the sort of point of having work graphs and this constant backend memory. And I'd say in both cases, it's a couple hundred megs is justifiable.
There might be another question. Yeah.
Okay, if I got the question correctly, you said in CUDA it's a bit easier to launch the different kernels, and WorkGraph seems a bit more involved with declaring what's the worst case you expect. I'm not sure if CUDA has this sort of managed memory as well. Because work graphs isn't just I want to launch new work. I have a work record or work item. I have some data to go along with that launch. And work graphs will keep track of this memory for you. You need sort of these limits in order to keep deadlocks from happening. Workgraphs also has forward progress guarantees. I'm not too familiar with sort of the CUDA alternative, so I can't really say why their sort of API is similar. A lot more questions, yeah?
When you have the node array, is that, if you've got a node array and it's got like 1,000 nodes, does that imply that you've got like 1,000 ring buffers?
There is some question was if we have node arrays, and I showed a slide where it says 1,000 for the node array size. Would that mean that we have 1,000 of these ring buffers in sort of a very primitive implementation you might have, but there are some optimizations you can do for node arrays. Yeah.
What happens to your cache subsystem? So there's no barriers, no memory fences or anything. So you have L2, but what happens above L2? So you just wipe it out? Because how do you track dependencies in your implementation across?
The question was on caches and sort of the memory writes to ring buffers, if I got that right. How does it interfere with caches? So if you write to the ring buffer, they live in global memory. If you want to ensure that sort of the command process reads the current state, you would always need to bypass caches. And then if you want to optimize, yeah, that's probably the best way to.
So basically to send data from one node to another, there won't be any cache.
With this, you could keep them in caches. You could sort of move some of the ring buffers to caches.
Yeah, I'm sorry. So further question is
we can talk offline.
Yeah, offline. Yeah, please.
I think we're also on time.
Yeah.
If you have more questions, just come to me.
Yeah. Thanks again, speakers. Yeah. Next speaker came from NVIDIA, so his name is Jefferson. Yeah, so formerly I work at Intel, so I personally met him. Yeah, so maybe he was some kind of the visualization expert, so he was leading some kind of the visualization product at Intel. Yes, and based on his deep knowledge, the experience, he moved to NVIDIA and as some senior dev tech and the setting of the new visualization standard in the kernel. So that is the main topic of today's talk. Yeah.
All right. Thank you all for being willing to listen to me for a half an hour, but I'm very grateful to be able to speak with you about Inari. And there's a lot that could be talked about with an API standard, especially if you're coming in cold. So my hope is that you get some familiarity with what Inari is, and understand that the portability and scalability goals of such an API spec would make it hopefully attractive for you. So I think the best place to start is what was the situation that generated the need for a new API standard. And we had the situation with 3D applications on the left and rendering engines on the right. And let's say you're a ParaView developer and you want to say, I want to use Osprey and ProRender and VizRTX. You end up having this problem that you, the application developer, has to learn how to speak to each one of those. Not a terrible problem to solve, but one that has to be solved. The problem is, if someone else, who's another application developer, wants to do the same thing, like Blender, you have to do the same work over and over again, and VMD, and et cetera. Just name your favorite app. You have to solve this problem. And I don't know about you, but that's a mess of lines, and it's only 3 applications and 4 rendering engines, and there's way more than that in our ecosystem. So the goal was to say, can we create an API that applications can talk to that makes all these engines look very similar, and can engines not have to know with who's invoking them to say, if you give me a scene and I can give you pixels, we can enjoy working together. And that's what Inari is. And in Karen's keynote yesterday on Vulkan, she talked about how Vulkan is not for the faint of heart. I think that was during the Q&A. And so that teed me up to say, Inari, it's for the faint of heart. So Kronos is a standards consortium that we probably have a lot of familiarity with, and it's been a great way to structure how do you get different companies with different IP to be able to work together on something, on what are the things we can agree on, and then how can we not prevent each other from having our innovation come out. So Kronos has been a great place to participate in a long-standing history of great standards development being done. And so the story of Inari really starts in 2020. We had an exploratory group before that to kind of generate enough interest around creating it, but in 2020, we launched an official working group. And that was at the point we had to commit to a name. And just so you know, naming's hard. And the acronym Inari doesn't mean anything, but if you really want it to mean something, I'm trying to campaign for it to mean Anonymous Application Rendering Interface. I hope that catches on. But for now, just accept that that's the name. And we started in 2020, and we quickly moved on to working real hard on the API spec. And so it took a little over a year and a half, or about a year and a half, to get our first 1.0 provisional specification out. But then what I wanted to communicate with this division of path is that every step of the way that we've been working on the specification, there's been software, an SDK that people could use and have it be freely available to get experience with. And so we had an SDK right when the provisional spec came out, and that moved on. We got lots and lots of experience. We talked about like what is our story with how do we work with other specifications, like GLTF has some great PBR specifications, and we decided to import those into Inari. And every step of the way, we kept getting more and more SDK releases to pair with these things. And so that brought us to the 1.0 launch last year. It was a really great time and very satisfying to say we've done all of this work. Now finally in August 2023, we can say we have an official 1.0 spec. And what that means is not that we've solved every problem for how do you connect a rendering engine in an application. What we've done is we've said we think we have the things that we don't want to change in the future, we have those locked down, and we are now much more wide open to what are we going to add to the specification for things that people view are missing. But like I said, every step of the way, still working on that SDK. And then an exciting development this year has been a part of these specifications is what does it mean to be an official adopter of a standard? And so we have an adopters program for Inari, like there is for other specs like Vulkan, OpenGL. And what that means is if you want to come and say, I'm an official implementer, and you pay a fee, and you get to basically use that brand, Inari, and have some weight behind your claiming that you implement the spec. That said, if you are not an official adopter, you're absolutely welcome to come and implement the API and ship your implementation. So the idea is the adopters program is a way for us to get some buy-in and some common infrastructure, because it does things like fund our conformance test suite and stuff like that. So that's an open invite to anyone interested in Inari that consider the adopters program. But like I said, things continue. We're working on more and more extensions every day. It's part of our 1.1 spec that I'm not sure when will come out. And our SDK, we've had a few releases, continues to mature. So at the end of the day, the cool thing about the Inari spec and how our working group has been functioning is everything, the spec and the SDK, are all up on GitHub. We're not trying to hide anything from anybody. And so we'd love to have you come participate, but I'll touch on that again near the end. So when you design an API, there's fundamental tensions you have to reason about, trade-offs you make. And the one that you get at this level of abstraction where Inari sits in the software stack is things that are uniform. So that's where you can get some guarantees of what are concepts that are going to be the same. And then how do you differentiate different features based on what you deem important as a vendor or as an application developer wanting to see, like, why am I choosing to use a particular engine? And so on the API uniformity front, they are fairly mundane topics, but it's important that we not repeat ourselves in incompatible ways over and over again. And that's what ends up happening when we all have our own APIs. The way you create an object, the way you parameterize it, how do you create an array, what's the ownership semantics of that memory? What's the scene hierarchy exactly that you build? How do you deal with concurrency and parallelism, your thread safety, your ability to overlap frames and scene updates? These are all concerns that I think semantically are quite universal, but then in practice, we end up doing things ever so slightly differently for very incidental reasons. So Inari seeks API uniformity on these types of topics, but then on the other side, we want to leave it wide open for feature differentiation. So for instance, the features you decide to implement at an engine is completely up to you. Inari is not going to get into a debate with a particular engine's features that they deem important or not. What it is, though, is if you have a particular set of features, let's all spell them the same way, is the idea. There's also performance. Performance is a really wide, giant topic, whether you're talking about frame latency, you're talking about scene size, that's technically something else that I called out separately here, but that's performance of memory and like hardware scalability, image quality, illumination, global illumination, all of those things are ways that your engine might be better than others, why you would want someone to use your work. And so how do you balance these two? This is a really tough question to answer. And we think we came up with a pretty good philosophy behind how you can balance these two things. And that's for Inari to say, you give me the what and the when, but I'm going to let my engine determine how that happens. And so the way that pans out, I think maybe is more obvious if you look at the software stack, which at a very high level looks like this. You have applications who use Inari. Inari is interfacing with individual specific engines, and then that's where you're going to talk to graphics APIs and hardware. And so I want to walk through this bottom up from a first-person perspective, because I maintain a backend called VizRTX, and I work at NVIDIA, and so I want to be able to reason about where is all of my software fitting in this hierarchy, or this stack of how I have to deal with all this complexity. And so from my perspective, maintaining VizRTX, I care about GPUs. So VizRTX builds on NVIDIA technology, builds on GPUs. This is hopefully an obvious one. But this is where the next level up is where there's actually a shocking amount of diversity. And I think that's a good thing at least some fundamental level. But I choose optics with VizRTX. You might choose other things in this list. You might choose multiple things in this list. Those are the ways that you get at hardware features ultimately. But what you end up implementing is an entire engine. The ways that you make those pixels from the scenes that you get from your application look like this. And so I come from a scientific visualization background. That's what I do primarily at NVIDIA. So in SciViz, we have 3 different rendering engines that you could take off the shelf and do some really great SciViz with. That's VizRTX, VizGL, and Index. And there's others. Those are all implementations that exist, but that list can be arbitrarily long, and that's one of my hopes in speaking with you today, is I want that list to be as long as it possibly could be. But ultimately, where Inari comes in is what you're buying into is the way that an application talks to you, not tells you what to do necessarily, but the way it talks to you is fundamentally the same. And so when you think about application architecture, so you have, whether it's a small research app that you're using to show off your research, or you're at a big company with a multi-billion-dollar application, I don't know. The point is that without this separation of concerns, things get very muddy. It's like if you write a 3D application, get ready to start writing Vulkan, is a very commonly held presupposition in 3D application development. So what Inari's doing is saying we can make this split such that you might be someone who doesn't care about implementing a renderer. You might just want to use Inari and say, listen, I want to offload that work to someone else. And likewise, it could be you have a very specific rendering engine for your problem, and so you might be an application developer and a rendering engine implementer. That doesn't mean Inari is going to get in your way. Hopefully that helps you organize yourself and then make your application actually more portable. So then this is the whole stack, not hiding anything. I think this is where there's a tremendous amount of diversity that's good to get a lot of great things, a lot of great research, a lot of great technology. So fundamentally, when you're talking to the Inari API, it's pretty straightforward. So it's a C99 API, so what you're going to do is you're going to compile against inari.h, which is going to give you a bunch of C prototype functions, and you have the front-end library, libinari, that you're going to link to. You don't have to have runtime loading of backends, but that's what generally people do. And so at runtime, then you can dispatch to whatever renderer you want. At the end of the day, all of those mechanisms are quite flexible. I'm really breezing over those details. Talk to me if this setup's a problem for you, but it's worked really, really well so far. And then just like Vulkan, we took a page from their playbook and decided layering is a good idea. And it turns out when you have an implementation you're talking to, that implementation could be just something in between you and the actual thing making pixels. So then you can do arbitrary things in that layer. And so we have a debug layer that can validate your API usage. Again, very similar to Vulkan, but that already exists today and has been proven quite useful. Okay, so a breeze through the API for how it might look. It's a C API. There's C++ type wrappers. That excites me. If it doesn't excite you, that's okay. The devices are what we call the instance of the rendering engine you're talking to. So this is the core thing, the unit that your application is talking to. And it usually can come from a shared library, but like I said, it doesn't have to. And so we're talking about 2 lines to get your hands on one of these devices. If you're going to load dynamically at runtime, you're going to say Inari load library, and we have a thing called a library object. And you load that, and that's going to do a dynamic load of a particular library and open it, essentially a DL open. And then you're going to get a device, or multiple devices potentially out of that library. The default's always going to be there, but there's ways for vendors to ship you multiple implementations from one library file. So a very, very core concept in Inari is objects. I mean, shocker, it's an object model for rendering scenes. So the objects themselves that you have, they're expressed with opaque handles, and that's very intentional to keep implementation detail away from your application. And we have 2 flows of information. Parameters are our word or our term for how information flows into an object, and properties is information that can flow out of an object. And the way this works is it's a transactional semantic where you say, I'm going to set parameters and then commit those parameters on the object, such as in the next frame, those values that are new will take effect. And what this does is a tremendous amount, gives us a lot of robustness for getting performance out of applications, but not having to prescribe very specific implementation details for mechanically how that works. And one note on parameters, that they're unidirectional. So one very quick design trap you can get into is if I can set a value, I want to be able to get the value out. The problem is that getting that same value out is prescribing quite a bit of implementation detail, especially in distributed context or in places you want to throw things on the GPU and not keep things on the CPU. And there's a million things that you could possibly do to want to diversify how you would implement that. So basically, it's like if you set a value, you know what that value is. Keep it around if you really want it, such as displaying it in a user interface. So just to get a flavor for how it looks to interact with objects, when you create some objects don't need a subtype. So like a world is just a world. Some objects do need a subtype, which makes sense. Like you have a diversity of different cameras. A perspective camera is a very obvious one, but it's pretty straightforward to basically reason about those. Setting parameters, again, I hope is a straightforward concept. This isn't revolutionary necessarily. So you have the device, the implementation you're talking to, the object handle of what you're operating on, the value you're wanting to set, and then the type and a pointer to that local value in your application to set it, where it's going to mem copy from that pointer. And then if you want those to take effect, you simply commit the object and move on. You actually know a shocking amount of the API just from that slide. Now, if you think, of course, we got to build a hierarchy. This is something that, again, should shock nobody, but it's frame-centric. So everything you need to render a frame lives under the frame. And there are some times that you have a single object relationship. Sometimes you create an array of handles. So like a world can have n different instances in it. That makes sense. This is something that I won't walk through every detail of all of these, but again, open the spec and have a look. It should be straightforward to understand. And then what we all came for, rendering a frame. What does that look like? Well, you kick off a render frame with Inari render frame. I hope we chose that name well. Then you can immediately synchronize with it because that's an asynchronous operation. You don't have to. Then you can map pixels out of a frame channel. You could write that to a file. You could put that on screen, do whatever you want, and then you unmap the frame. So really, you have most of the API's concepts now with these couple of slides. And that's really all you need to make cool pictures, to make interactive pictures, real-time pictures. The idea is the API is not not the one responsible for telling you how do you do all that cool emissive materials stuff on those streamlines, animating those. That's all just stuff that the engine's doing for you. That's the whole point. There's a bunch of topics we could get into that I don't have time in a short 25-minute talk. Like, what are all the different subtypes that are available in the spec? What does it look like to add additional ones that aren't yet in the spec? Geometries, materials, samplers, lights, there's tons to talk about. Device introspection is a great topic where you can ask your implementation, hey, what do you implement? Because I may or may not want to use you based on having a particular extension that I care about. The whole asynchronous piece is one I just blew over, but there's a lot of cool application architecture discussions you could have about leveraging that and exploiting that well. What does it look like to have multiple viewports in one app and maintaining all of that either from multiple devices or a single device with multiple frames? Arrays, performance considerations. There's just a lot of things to talk about that we won't be able to get to. But then what I want to give you is a sense of these two opposing forces and how they both can be leveraged really well. And so the first one is that Inari is portable. So the API uniformity that we get in the things that I say don't matter in terms of diversifying those choices, the things we lock down make it so every time we put Inari in another application, we get the same story. And like, that's the whole point. Like, if you want one takeaway of why would I care about Inari as an application developer or as a rendering engine implementer, it's you implement once and you can get carried into places that you might not have ever considered simply because you bought into a standard API. And so Blender, we've done some experiments and cool things in Omniverse, ParaView, Visit, VMD. This is just a short list. There's so many more applications that I haven't listed. And one I wanted to point out is there's a lot of little apps we write for our own little renderers when we're doing research, we're doing other application development, or maybe I'm developing my renderer. I love Dear MGUI. It's a wonderful UI library. I write apps all the time. That's just a generic Inari viewport. And even though I made that app to develop VizRTX, I can run any of the other implementations available equally as well. It's a great consequence of buying in to a standard API. But on the other hand, scalability is a very important thing to not lose sight of, because scalability means different things to different people. If you're an offline renderer, scalability means I need to be able to make those pixels as pretty as possible at whatever cost. You could say that scalability is, I want to use as much hardware as I possibly can. Like, if you're in an HPC cluster environment like me, you might be wanting to use all of the nodes in that cluster to get as fast and as beautiful pictures as you can. There's different render rates. Like, if you're in VR, those render rates are so important to not get sick. Like, it's really important. Scene size. There are limits in all kinds of different engines, but Inari doesn't basically enforce those limits. It's just when your engine's done, it's done. And then, of course, animation updates. Like, that's a whole topic in and of itself that I'm blowing over for the sake of time. But yes, that's something you can choose to be the value that your engine brings in, being able to tolerate animation update rates that are really fast. And so I wanted to tell a really brief anecdote about how research and Inari can fold together really well. And many of you know Ingo Wald. He and I go a long way back at Intel and at NVIDIA now. And he wrote a couple of papers on distributed memory path tracing at HPG. 2 years ago, he had a paper on basically ray forwarding based on object hierarchies. That was a cool paper to read. And then also some follow-on work last year about ray queue cycling amongst multiple GPUs and a single node to get all of the memory parallelism or the full memory available to be able to render with. But then there's this renderer that he created called Barney, and it's up on GitHub, and you can go get it today. The problem is, what if you want to put Barney in a bunch of different scientific visualization applications to get it in users' hands, to get access to their content? Like, that's a big problem. And I convinced Ingo to maybe try out Inari. And so what we did is we looked at this stack, and if we looked at it from Barney's perspective, it looks like this. There are all these applications that use Inari. Then Barney is the rendering engine. It uses CUDA optics and MPI, and it builds on GPUs and fast network interconnects. And then with that, it was shocking how little work it took to get these production applications with production data sets on hundreds of GPUs sometimes. Like the DNS volume, I think that was 128 GPUs that a colleague just ran it on because it just worked. It was shocking how straightforward it was to get this running in environments that were probably any other way would be really hard. Be a lot of software engineering, a lot of figuring out how to get environments to work. Inari just made this so easy. It was almost like something has to be wrong. But that was a really cool outcome. And if you want to read details about that whole narrative, we actually wrote a paper on this where it's at LDAV. It got accepted to LDAV this year, but we have a preprint up on ARVIX called Standardized Data Parallel Rendering Using Inari. And the point is that we were able to take the Inari API and take its semantics and inject a few extra constraints, no API calls, to be able to have a very tight understanding of every distributed rendering architecture we could think of fit into these semantics such that we could more definitively say, if you implement the Inari API in a distributed context, there's no need to invent any other interfaces for these applications. They just work. Again, read the paper for more details on that. And so what I want to leave you with are some calls to action, because this is a room full of very bright researchers, some people that have done some amazing work, and there's a lot of discussions about how Inari could bring you value. The first basic step is just to try out the SDK. Something as simple as get familiar with how the API works. Just try it out. Try out some backends that are up there listed in the README. I'm hoping it's a really straightforward process to just see, make, and voila, you have an Inari SDK built for you. There's some interesting backends that are available today. There's VisRTX, Osprey. There's a research renderer called Visionary. It's a nice path tracer that Stefan Zellman wrote. We have Ingo's Barney renderer. I have a prototype that works with Cycles renderer out of Blender. There's a lot of exciting work already available today to try out. But the more I guess important thing I would like to implore this room to consider is if you're sitting on a renderer, as small or as big, you could be doing it just for fun, you could be doing it for big production reasons. I really want you to consider what it would look like for you to look at maybe supporting Inari as an option for your engine. That's a really big, wide open statement, but one that I think if you start walking towards the benefits of the API stability and the scalability, the differentiation that you want to bring to our ecosystem of 3D graphics is something that if we all simultaneously walk towards, there could be a lot of even more exciting future HPGs. We could be talking about all kinds of great diversity of implementations that everyone could try, that we aren't just holding on to for ourselves. And then actually getting involved with the standard is not actually that bad. If you work for a company that already is a Kronos member, you can just come join the working group. It's as trivial as that. You can see our meeting times, 10 a.m. Pacific on Wednesdays, and we'd love to have you come participate. Even if you just come listen, it's like little half-hour calls. It's not that much overhead. We also have an advisory panel, and what that means is if you're a non-Kronos member, we still want to be able to talk about interesting design decisions with you. And so Kronos has a very well-oiled mechanism for how do we make that happen, so you can still contribute in those kind of design discussions of the API. And then, of course, at the end of the day, if you use the SDK and you don't even talk about the spec itself, and you just use it, and you come up with an issue, we'd love to hear from you on GitHub. And so with that, I'll just wrap up by leaving this up to say I'd love to start a dialogue with you now. Probably don't have a ton of time with questions now. I'd love to talk with you in between other sessions about what Inari could mean for you. So appreciate your time and would take any questions you have.
Yeah, cool. Yeah, so questions for Jefferson? Oh, there's.
Yep. So I'm interested into teaching. Do you think Inari could play a role in teaching about graphics programming, and how would that be?
Absolutely, for two reasons. One, when you're teaching someone who doesn't have familiarity with hardly anything, it's actually good to lock some things down, to say, you know what, don't worry about designing how parameters get set. Just buy into this and worry about some other things. I think that's a valuable characteristic for teaching. The second is, if you get someone implementing the Inari API, it's a really strong hook to say, oh my gosh, I just ran it in their Blender add-on and it just worked. And I didn't even have to figure out how Blender worked. Like, that's a really cool outcome to get people hooked on wanting to do stuff. So I think that's a great avenue for sure. Others?
Did I get it right that Blender already use Inari for Cycles engine?
So that's technically possible. They're both pretty much in their infancy. So with Cycles, it's pretty much my ability to figure out how Cycles works as like a nights and weekends type thing. I have some people who are interested in wanting to take that into a more production context. Then on the add-on side, that actually is implemented entirely with our Python bindings and using Blender's Python API. I'd love to push that towards a native implementation that lives in Blender. And then my hope is if those both mature, then they both basically get to a point with it. You can do everything today, but in that context, but then Cycles is now usable in all these other contexts.
I see. Second question is, does Inari support multi-GPU configuration of multi-GPU boxes?
Yeah, absolutely, because that's part of the implementation detail of an engine. So for instance, Barney, like it's built to be multi-GPU in multiple ways, and the idea is you would basically ask Barney, what are your device parameters to control of those things? And then once you have that set up, everything else is identical. So absolutely, yeah.
Hi. In the film and VFX production world, there's universal scene description, which is meant to act as a crossbar, kind of like this. How would you compare?
Yeah, so I'm going to be very careful with my words and very politically correct. Not for the, because I don't want people to get the wrong idea. So we have a Hydra plugin, but the idea of Inari is it's only about rendering frames. So something like USD is looking to solve a lot of problems, and a lot of problems that Inari will never try to solve because it's just not the point of the specification of this API. I'd say the closest comparison you could make would be, this would be like the same type of API of talking to a single render delegate in Hydra. So all the scene delegate stuff, still, we have nothing to say there. They're not looking to get into that. It's really, if you're going to talk to a single renderer, you would use an API like this. The rest of USD, not trying to go there at all.
Other question? Yep. Yep, please.
You mentioned that there was a validation layer. How complete is the implementation of that application?
Yeah. So
could you reproduce?
Yeah. To repeat the question, that there's a validation layer, and how complete is a validation layer? And validating Inari has this cool property that we already have built into the API that you can ask your device, what do you implement? And that gives you everything from object subtypes, parameters, their ranges, all those things. And we can actually have the debug layer just ask the device, give me all that information, and now I can validate application use on what the device is reporting. So the debug layer doesn't have to be the sum of everybody's implementation extensions. It can actually be done device for device. So there's already a ton that you can debug that way. We haven't gotten into any like concurrency type validation yet, but most of the problems people have at this high level of abstraction is, did I spell the parameters right? Did I give them values that make sense? Did I make the hierarchy right? And we can validate all those things today. Yeah, so we have very, very rudimentary API replay. I'd love to see that mature like crazy because that's a really valuable tool to have. And I think some challenges we have are going to be in a lot more of the concurrency stuff. That said, the API surface area is a lot smaller. We're solving a much simpler problem to express. So I'm actually hoping the complexity is actually hits a reasonable ceiling at some point.
One last question, so I don't want to hurt your break time. So last question.
Yeah, so
Question.
yeah, the question is, it's string-based parameter names. What standardizes that? One is we have core extensions and we have vendor extensions. Core extensions are ones you would look up in the spec and say, I have a perspective camera, and here's the parameters that it can be set on that. And when you ask your device, if you implement the perspective camera extension, that's the subtype and the parameters it can expect. You can get that all at runtime if you want. And the same thing is true with vendor extensions. All a vendor extension is an extension that comes into existence that's not in the Chronos spec. We expect those to exist all over the place. The most important thing is, design-wise, is we didn't want custom things and standard things to look different. And so we didn't want to go we want an API call for everything in the spec, giant API. And then we also wanted to leave things really open for extension. And we found in practice, it doesn't actually trip people up as much as you'd expect. And if it does, we have a debug layer to exactly validate those things.
Okay, thanks, speaker again. So maybe let's break. So please come back 4:30, please. Yeah.
Hello, hello. Okay, all right. Welcome back. So let's start our second keynote. It's an honor for me and for the conference to present Peter Schiller as the second keynote. We're very happy to have Peter as a speaker in our conference. I think Peter, everybody knows Peter and you don't need presentations, but I will anyway present. Peter is a vice president of computer graphics at Activision. He's former researcher at NVIDIA, co-founder of two companies, software companies, and professor of Indiana University and Cornell University and University of Utah. He received his bachelor in physics from Reed College and PhD in computer science from University of Illinois. He's co-author of several books on computer graphics and a variety of technical articles. He's also a member of the SIGGRAPH Academy. I think Peter's, everybody from education knows Peter as, and all his books and all his materials, which are wonderful. And I will just mention that, sorry for mentioning this, but Peter, when we invited Peter to be keynote, he mentioned, of course, HPG is one of my favorite conferences. So we are very glad to have you here, Peter, and thank you very much for speaking here. Okay, let's welcome.
Thank you. Is this mic on? Mic is on? Yes. It is one of my two favorite conferences. One is Rendering Workshop, one is this, and they go back and forth. But my favorite thing about this conference is the undercurrent is studying things that work, which most conferences don't. So, and I'm a fan of things that work, which is one reason I've gone to a game company. So this talk, I gave the title to force myself to do this homework, because until a year ago, I was not a real-time graphics person, and I've gotten really a deep immersion in it, and I don't really know where it came from, because when this stuff was going on, I was doing other things. Now granted, the first part of this talk will be stuff I am familiar with, because a lot of 60 FPS graphics is just batch graphics from 30 years ago, made fast by hardware. So this is past the University of Utah, and this is not that long ago. That's how young our field is. And the part of the past, I'm not going to do a full coverage. I'm going to only cover things that people actually use. So like the saber-tooth tiger, it's super cool. That tooth innovation algorithm didn't work out, didn't last, wouldn't cover it. The risk of that is if this were an AI talk 10 years ago, I wouldn't mention neural nets. So it's a little risky, but I'll just talk about things we use now. A lot of our graphics history really comes from film and TV, and this is an awesome book which I have finally read. He really goes into depth, so get ready when you read this and sit down and concentrate. But it is a wealth of information I did not know about where did the roots of our field come from. And first of all, here's like the first graphics in my mind, which is when they said, hey, let's do this moving picture stuff, empirically, how many frames per second was needed to make the illusion of motion happen? And the empirical answer was 16 frames per second. And then they had to figure out a way to project this on some kind of medium. And this is a remarkable engineering device, something that shows you a frame for about a 16th of a second, and then advances so you don't see the blur, so some shutter mechanism has to happen. Go look at, if you aren't familiar with how those projectors work, go look at it. It's really an amazing piece of engineering. Like the sound is on the same film strip, but it's stepping along stopping. And so how would you design that? It's actually pretty hard to come up with. Probably true from the internet, though I can't fully verify this, these would flicker if it did 16 frames per second, and that's why they call them flicks. And the innovation was to just have the shutter go multiple times, so the strobing was at a different frequency than the actual film advance. Super KISS solution to this problem. And then we go to games. Where do games come from this? Well, games wanted more than 16 frames per second. The empirical result is story-based games are 30 frames per second. Some of that is due to the history of the television set and its natural frequencies, but about 30 FPS seems to be a good number. But there's a different part of graphics, which competitive video games and things like flight simulators are. They need 60 frames per second. That was kind of established by E&S with their flight simulators back in the day, and that was just an empirical result, and seems to have lasted. 60 frames seems to be kind of a sweet spot where it's good enough for your reaction in a simulation or in a game combat, but it's not so bad that you can't get a good image quality. And then let's just look at what's happened to movie and TV and the parallel evolution that is highly related to computer graphics, because we often use their displays, so there's some divergence. And where's that gone? And the surprising thing to me is 24, 48 frames per second has been tried. 24 frames per second really seems to be preferred empirically. And when people try to do more than that, it fails in the market. Now, maybe that doesn't mean it won't succeed in the market in 10 years, but just a quick survey. Who saw one of these high frame rate Hobbit or Avatar things? Unfortunately, I missed them. Who saw them and liked it better than traditional film? All right, I want to talk to you at the reception, because I want some fans, because I have no dog in this hunt, because I didn't see any of these things. I was just interested. Okay, let's switch to geometry. What's happened in geometry in the past? All these different things have come along that people have tried. This will be the shortest part of the talk. Triangle 1. I never would have predicted this 30 years ago, because, you know, it's a really bloated representation. It's kind of awkward to tessellate something. We have higher order surfaces, which just will need more computation but less bandwidth. That seems like it's a good future trend. Man, those triangles have staying power. So we'll discuss that no more. How about the graphics pipeline? This, to me, is the OG of computer graphics. This is Larry Roberts. Quick survey, who's heard of Larry Roberts? I think this is a crime. I think this should be who we talk about first in computer science. And he should have won 2 Turing Awards, or maybe 3. So here's from his 1963 dissertation at MIT, same year I was born. And look at that set of matrices. This dude isn't even a graphics guy. He's doing computer vision, and he pulls that out of somewhere. I have not tracked down like what the source for that is, and did anyone use matrices first? So I'd be interested to hear. Quick digression, anything incomplete or wrong in this talk, I want to hear about it, and I will iterate. This is version 1.0, so I'll iterate this. But if you look at this guy's Wikipedia page, he is the father of computer vision. And if you look farther down the Wikipedia page, he is the father of the internet, because he really pushed packet switching networks, both technologically and deploying them. Like, he made that happen politically, and he did this. So I would argue he has a good candidate for father of computer graphics, and no Turing Award. So if you're ever complaining you don't get enough recognition, man, just think of Larry Roberts. Now then, a lot of the algorithms that underlie current real-time graphics were done as batch algorithms back in the day. Most of them at the University of Utah in this ugly old building, which I've worked in before. And this is not a great building. But Ivan Sutherland, pictured here with Dave Evans, he said that through his long, successful career, his experience empirically is that the quality of work done is inversely proportional to the quality of the space. So when somebody in your organization proposes that, oh, we were so successful, we should build a new monument to ourselves in the form of building, say, no, scholarships, let's do that instead. And we got all these familiar pictures of various things, you know, bump mapping, et cetera, out of that amazing time at Utah. But there was some stuff going on other places than Utah, like the first physically based rendering paper, in my opinion, was this BRDF paper from Cook back in the day, which he did at Cornell. And the backstory on that is he's like, wow, I needed to look at light reflection. I'll go find out who on campus knows about light reflection. And he went down to another building and found Ken Torrance. So if you're a student, go looking for somebody on campus that like knows something you don't. It's a lot easier than like reading books. So here's the summary. Here are the golden age inventions. And the part that surprised me the most is The cosine raised to a power highlights were being done commonly at Utah in the late 60s and were first done apparently by a fellow named Romney. Phong did normal interpolation. So in preparing this, I was like, surely I know these things, but no, there was some basic stuff. And that was in Garot's paper, so it wasn't like an obscure thing that this was being done. Who already knew this, that cosine raised to a power predated Phong? Okay, I'll buy you a beer. One person. All of these things are just used commonly in real-time games now. So it's interesting how much staying power these things had, given how much has changed in computer science. Another candidate for, I guess he did win a Turing Award, so we can't say he was underappreciated. It's Catmull in one thesis did Z-buffer, subdivision surfaces, and texture mapping. So that's unbelievable. And one of the members of his committee wanted to stop him from doing sub-Ds because that was clearly such a bad idea. And Catmull won that argument by removing him from his dissertation committee. So remember, KISS algorithms work. And then ray tracing came along. That obviously is used commonly in interactive applications. And if you have enough hardware, 60 frames per second, no problem. Whitted, also Kay did this in a master's thesis around the same time. Whitted did the more complete implementation, so he usually gets credit, I think deservedly so. And then Cook came along and said, let's add a call to random number generator in Whitted's ray tracing program. What's interesting here, too, is if you read Cook's paper, he said he got the idea from Whitted's paper, and I'm like, he did? I thought I read Whitted's paper. But there's a little bit in Whitted's paper. Look at that random thing. He's talking about randomly perturbing rays from surfaces in that 1980 paper. It's just amazing. So read papers carefully. Often they will just give you gold in there. That 1980 paper also had bounding volume hierarchies. That's just incredible. It's an incredible paper. And then the physically based rendering stuff from Cook with BRDFs started this movement at Cornell to really dig into the physics, and they were talking about, hey, let's look at light interreflection, not just for mirrors, but also diffuse surfaces. And this also was the second paper I'm aware of. There was actually a super old Utah paper that had this, that actually tried to do a comparison with the real photo. That very brave thing to do. And that spurned a radiosity feeding frenzy that's kind of like the Nerf thing now, where there was just a ton of radiosity papers. And the advantage of radiosity at the time was, hey, we have these Garot shaded triangles on hardware. We can just spit out the illumination at the vertices of these things and just do Garot shading. And a lot of that was pursued to try and reduce the number of triangles. So this is just a particular radiosity mesh where, though it's stored in the mesh, is not geometry, but the illumination at the vertices. And you can see that there's more tessellation, like in the shadow regions. And where there's a contact shadow, there's a lot of meshing. So there's a lot of work done on that back in the day. And that hasn't lasted so much. But what has lasted is baking. So this is saying, hey, let's pre-compute this lighting, put it on the diffuse surfaces, and not recompute it as we change our viewpoint. And baking is just a great trick. There is baking in real life. So you can always take illumination and replace it with albedo, and no one will know the difference. It's just a classic imposter strategy we use all the time in graphics. What looks the same as this real thing, but is faster to render. So these are real photos. Some artist painted a shadow, remarkably convincing. This is the Samsung Frame, which is a TV that has a light sensor, and when you put it in screensaver mode, and it's very flat, it tries to make itself look like a reflective surface with a certain pattern for that light level. And it's not perfect because its sensor is not quite good enough, but if you tune it, it really looks like a reflective surface in real life. So this imposter thing, I think we should often think more about what environment are we actually building? We're doing a physically accurate representation of some imposter environment that looks the same. Often, I think, leads to a cleaner way of thinking about the algorithm. Okay, baking is more usually done with texture maps, illumination maps. This is the first one I could find, which is Jim Arvo back in the 80s did this paper. with illumination maps, and he did it, of course, for caustics, which would be way too slow to do interactively. Still, that's a super challenge now. The trouble with baking on surfaces is you would like, in many circumstances, to have dynamic objects walk through a baked environment. Like if you baked this room, then you had a character walk through. The character wouldn't affect the room so much, but you ought to have the room affect the character. And so you can bake into a volume. This is a commonly used technique now. So you just query a 3D texture, essentially, to look something up. The way this is done at Activision, by the way, is being presented tomorrow in Natasha's course tomorrow afternoon by Michael Ivanicki. I think he's very close to solve the light leak problem. Like, we're not going to look into that anymore. I think that finally is nailed enough. Super cool method, so you should check out his talk tomorrow afternoon. Okay, interactive ray tracing. That was first done, to my knowledge, 4 frames per second, so we're being a little generous, by Mike Moose at the Army Research Lab. Some of you old timers remember BRLCAD, the first distributed on the internet ray tracer, I think. Who's used BRLCAD here? Anybody? Okay, we're going to have old timers reunion. And who knows what Mike Moose is better known for? Sadly, he was killed in a car accident, and he's no longer with us. Yes? Ping, that's right. This guy wrote Ping. So he did the first interactive ray tracer and Ping. I'm impressed. I know what I would have on my tombstone if I were him. And then someone said, hey, yeah, sure, Mike Moose, you can do this with like a $100 million computer. We'll do it on a PC. In fact, I think 3 of the authors of this paper are in this room, right? Can you raise your hand? 1, there's Philip. 2. Yeah, well, then this was a very impressive paper because it was like 5 years sooner than any of us thought would happen. And that really, I think, changed the bits in some of our brains for like, how fast could you do this? And then Philip's same lab did this thing of, well, what if you had special purpose hardware? Let's take an FPGA and just run it. And it ran interactively on this one FPGA. It was super impressive, which kind of demonstrated if you did have special purpose hardware, ray tracing could run very efficiently on it. And then the real key invention to make interactive ray tracing practical, since you really want Monte Carlo ray tracing, not just ray tracing because you want diffuse interreflection, is you need denoising. So this took me quite a while of archaeology with Google Scholar. Who did the first let's denoise a path tracer paper? I have a candidate. Does anyone know? This is my candidate. So if you can find an earlier one, I want to hear about it. Henrik Jensen did it back in the day, and all of us were offended because it added bias. Clearly a bad idea. So I would say one of the biggest, I think it cost us 5 years in the research community that we Monte Carlo people viewed bias as a bad thing. If we could have removed that, Puritan block from our head, we would have gone a lot faster. Henrik apparently didn't have it. And then along came ambient occlusion. This to me is like kind of a meteor in that it was completely offensive to the physically based rendering people. It's just a hack that darkens in the corners, but it actually looks better than the correct physics because it also kind of looks like you're putting dirt in the corners, so it like fixes these models. And it was actually called obscurance in this original paper. I'm not sure who coined ambient occlusion. I kind of like obscurance though. So it's not a bad term. And that to me kind of told us not only is bias sometimes a good idea, but just completely incorrect physics that accomplishes the task is a good idea. Then I would say this next candidate, I'm giving a tentative, it's had a big influence, but we're still early on this idea. This is coming up in a lot of places. It's a super clever idea, a nice simple hammer that just is good. If you haven't read this, I suggest you take a look at it, because if you're like me, where you read these modern graphics papers, I'm author on some of them, and you just see all these integral equations, you say, wow, I wish I were doing something else. This paper's kind of nice, and it's kind of old school. Let's use some simple math to really accomplish some good stuff. Okay, that's graphics algorithms. Now let's talk about materials. So materials we've always had a rough relationship with because the models don't really have all the right properties, but if they do have the right properties, they're too complicated. If we use microfacets for real, it's a pain. And then Brent Burley came along and he implemented all of the reflection models papers. I mean, literally all of them. Looked at the Merle database to see what worked, ran things past the artists, and then wrote this paper. And what year is this? 2012. So this is now a 12-year-old paper. And as far as I know, 100% of graphics people are basically using this method. I've never seen something take over the field more rapidly. Every video game, every movie, all the graphics APIs use this model. And here's the model if you're not familiar with it. There are 4 kinds of materials in the world. There's a diffuse and specular one, and if you want just diffuse, turn off the specular. That's that pot. There's metal, there's glass, and there's everything else. The everything else is the kitchen sink component of the model and kind of the weakest part, but the everything else we mostly don't care about unless it's skin. And so that everything else thing, I think there's still some work to do. Usually subsurface scattering is your biggest issue more than exactly what that surface term is. But this just works. And then further, he said, hey, instead of having a category of 4 different models, we'll just do this very complicated mixture of all 4 of these things. And it's not just mixing, it's a layer-based mixture model. And it's very complicated. And nothing is all 4 of these things. So this is a little offensive at first, but in practice, this is just what works. So if you look at old school renderers, say from 80s, 90s, they use different categories of material and have different, more efficient implementations. Almost all modern implementations have every single material all mixed together with some weird kludgy stuff. And that's usually called an Uber shader. And it's just taken over, so I've just accepted this now, even though at some level I don't like it, it works. As far as I can tell, the first Uber shader was Sing Fu at which studio? Some studio. None of this is documented, so that's oral tradition. If someone knows who thinks they did the first Uber shader, I'd like to hear about it, because that was a super influential idea that we just haven't tracked in our field. That sheen term, the kitchen sink term, Brent wasn't fully satisfied with, and neither was anybody else. So Sony did an improved one, at least they thought so, and their artists thought so. And then Brent has, well, not Brent, Brent and some of his colleagues have done a still yet more improved sheen term. I have not implemented the Sony or new Disney term. If any of you have, I'd like to hear about it. That's one of my side projects. At some point, I'd like to know, so is this good enough? And notice, linear transform cosines. So that gets to go in there. So that's a bunch of algorithms and BRDFs and 5,000 modeling papers where I had one slide that says triangles win. Then we started, like right now, if you look at a lot of what we see today, it's Monte Carlo rendering that's denoised. So where did that really start? That did not start from the ray tracing people, that started from the raster people. So they started taking taps, random taps, using rasterization, and that produced a noisy rendering, but one that was a very Monte Carlo one. And so I was off doing ray tracing at this time when this all went down, and I think this is of the last, say, 20 years. So in this millennium, the most important thing that happened in rendering is this raster-based do taps, do TAA, do denoising thing. And we don't really know where it came from because none of it was from the academic community. It all came from the games community. So it was published, and so I spent about 2 weeks asking around Activision and other game companies, like, who did this first? Who did screen space taps first? As far as I can tell, after 2 weeks, it was done by my boss in the next office first, along with some of her colleagues, and published in these books I don't own. So this is one reason I think the provenance on where these ideas came from is a little sketchy, because the games community published in strange places that the university people, like me at the time, didn't read. And so this, as far as I can tell, were the first papers doing depth of field and haze, but it was too slow. So it was like a very advanced technique that didn't quite work in practice. At least it didn't have a high enough frame rate. But around the same time, temporal anti-alias came along, an idea that I thought was just terrible because, let's say 1987 to 2007, there are dozens of failed projects trying to do time coherence between frames. It's a very attractive idea. And didn't work. But then someone started getting just the right mojo together to get it to work. This, thankfully, there is some provenance on because of a nice survey paper that was done. And as far as I know, these are the first 2 papers that did TAA back in the day. For those of you that don't know it, it just means, hey, don't just render a picture. Take the last several frames and blend them in with this picture. So this picture might just contribute 1/10 of this pixel to what's happened before it, and keep track of like camera motion and object motion so you can mix all of this together and hope the artifacts aren't too bad. It works way better than anyone expected. I think 100% of video games use this now. That may be wrong, but a lot of them do. And so the ideas from Natasha and her cohort in the previous slide, that started getting applied to other dimensions. And then it came out in games. And as far as I can tell, these are the first 2 places that actually produced a workable algorithm that you could do, well, 30 frames per second. Back in what year is this? 2007, 2008. There were other ideas from this Crytek engine, like I think this was the first thing to do effective screen space ray tracing, but I'm not positive about that. But this is where like the super hardcore Monte Carlo people, one was in raster graphics first for interactive applications anyway, and still winning. So this is, to me, this is like the culmination of a super incredible period of computer graphics research that most of us just weren't that aware of. It just happened off in that community that was not publishing in SIGGRAPH. I don't know if they were submitting, but they weren't publishing. Then another idea that was similar is, well, if you can do TAA, why not blur spatially too? And here's a paper, Alexander Reshetov, you're here probably still. Did you stay for my talk? I'm gonna be angry if you didn't, okay. And this was a paper I was like, that works really well, but won't it have terrible dynamic artifacts? Again, like we really anticipate a lot of trouble that once you tune things right, we didn't have. And so here's a paper that combines the TAA and the spatial anti-aliasing, and that's kind of the grandfather of things like DLSS that we have today. So this was news to me because I wasn't attending this much to this industry at the time. Blurred Monte Carlo rendering was already common 10 years ago. Then this company called NVIDIA came along and made effective ray tracing hardware. And then there was a AAA game that, as far as I know, this is the first AAA game with widespread or like, ubiquitous ray tracing in it. And specular reflection, I'm sorry, it just doesn't excite me that much. So this one I was like, oh, that's super cool, but where's my diffuse bounce? But soon enough, it came along in this game. Which I've heard is a good game, so it's on my list to like someday actually play. It sounds dystopian enough for my taste, and I think it's set in like 2030 or something, which is pretty funny. The bounce you see on the ceiling there is from the illuminated patches down below, so they're actually doing a 1 bounce path trace here. Very effective. Okay, one last thing from the past. Another thing that came in from the side is, you do this physically based rendering. And by the way, almost all movies and games now are physically based, even if their final goal is not absolute realism. That's just kind of interesting and, to me, unanticipated. But you need to tone map this sucker at the end, which means you need some form of perceptual optimization, either empirical or from science. So I'm like, oh, okay, so you do some kind of tone mapping where you have a model of the human visual system and you optimize the display, given it's the low dynamic range. I'm thinking, this is a very modern idea. Like, who had that first? And I thought it was like Tumblr and Rushmeyer back in the 90s, but where was it? Anyone know? This one kind of blew me away. What? It might be, but the earliest I know is this one from University of Utah in the early 70s. It's unbelievable. He took a human visual model and he did dodging and burning basically to take the high dynamic range negative down to a low dynamic range positive. And this was Jim Kajia's advisor, and if you look in Jim Kajia's dissertation, it's like a big giant human visual system model that stemmed from this kind of thinking. Then I think this was largely forgotten in our industry, sadly, but it was revisited by Jack Tumblin and Holly Rushmeyer. And this is the diagram that I still think of when I think of tone mapping. And that was the thinking in tone mapping for many years. Let's actually use, and this is a very academic way of approaching it, it's the way I approached it. Let's take a mathematical model of the human visual system and optimize the output for that. And the problem is the mathematical model of the human visual systems kind of suck. And so you end up with a fairly limited thing. And what almost all of these perception graphics works do, including all of mine, is you say, oh, apply this cool model. Oh, but we have some knobs to tweak. And then you use your n=1 experiment in your own system to get something that you like. And so I think now people are more leaning into, let's cut out the middleman and just steal from the artists. They've been doing this for 100 years. They have a bunch of standard practices. And that's now what's done in most tone mapping, is you just take what the film industry did and steal it. And it seems to be working pretty well. So that wraps up the past. That's my whirlwind tour of the past. Where do we stand now? So here is our present. This was my favorite meme from the last 4 years. And let's go to what screens do people use right now? So here's where people look at images. Now what's interesting to me is they don't look at stereo at all. And this was very disappointing to me a couple years ago at NVIDIA. I wanted to do a stereo demo. I could not buy a stereo machine, or a stereo screen for any amount of money. 10 years ago, I could have walked into any Best Buy and had a choice of 3 different manufacturers' stereo screen. So I think stereo to the consumer is something we can say we very confidently have done an experiment to determine they don't seem to want it, which is disappointing to me personally, but everything else is on the line here. The phone is particularly confusing because the screen is small, and VR is particularly confusing because it's just a different paradigm of looking at stuff. So let's go to gaming on these devices. Almost all games are now 30 FPS or 60 FPS, and that seems remarkably stable. And the fractions of games that are 60 FPS is smaller than when I joined NVIDIA first in 2008. So what is that? 16 years ago, computing has improved a factor of 1,000,000. The frame rate has stayed the same, and the fraction they're doing 30 FPS has gone up. This would have been very surprising to me if you told me that at the time, but that's very interesting. What's also interesting is people prefer 24 frame per second films. Like you go watch an old film, it's pretty low dynamic range, it's dim, but man, they look really good for some reason. Is that because the medium is so well established that that they have great practices for 24, so it's in some local minimum of production? Or do we have natural frequencies, and maybe our cinematics in games should be 24, not 30? Has anyone tried this, by the way? I was thinking someone must have tried this, because you get the motion blur right, you get 24 frames per second. Most consumers now own a screen that will go 120 hertz, so that divides evenly with 24, so you could do this. Would it look better? And so one question is just, that seems weird. Do we have natural frequencies, really? And I only recently learned that this was a thing. In fact, Chris Wyman here in the audience, I was talking to him about this work, and he said, well, that would explain Moiré patterns that you see in real life. And I'm like, dude, you need an MRI or something. You see Moiré patterns in real life? You see like wagon wheel effect? And he's like, oh yeah. And so I started reading, and a lot of people see wagon wheel effect in real life, which I did not realize. One circumstance where it happens is you're riding a car and it's bumping along and so your eyeballs are physically bouncing, and that can cause some wagon wheel effect for the car next to you. But it also happens people are totally still. And it turns out the psych people have been arguing about this for like 50 years, and I was just unaware of the argument. This is the most recent readable paper I have been able to find. And so apparently there are circumstances where we do see natural frequency effects as if we have some Hertz thing going on our head. And it's an argument why it occurs. Some of the psych people think, yes, it's true, but it's nothing deep here. It's because your skull has a certain radius and there's certain literally speeds that things are traveling, and so you end up with a natural frequency. But I think this would be a very interesting thing is, does 24 look better than 30 if you do everything right? And if you have a 120 Hertz monitor and are a very good graphics programmer, I think you could do this experiment. There's some other questions I have too about the present, like why are movies so dim? They could be a lot brighter. I don't think I'd like it. Is it just because I don't want to see the rest of the people in the audience? If you made it any brighter, it wouldn't be that movie experience. I don't know. Why are TVs still dimmish? So the current TVs are about 400 nits. Plenty of people have demonstrated TVs at 4,000 nits. They're very producible. You can cool them. Nobody seems to want them. And when I've seen them, they look really good. So is it because they consume too much power? Do they cost too much to manufacture because they're just more expensive? I don't know the answer. But I've had a 4,000 nit TV and a 1,000 nit TV in the same lab, and the 4,000 nit TV just looks better. And neither of them are like excessively bright. Maybe it's you don't want to watch them for 4 hours. It could be as simple as that. But I find this very confusing. The 16,000 nits is the brightest screen I have seen, and it looked good. So this is just a mystery to me, why the TVs haven't gotten brighter. Okay, and where do people render their graphics now? All over the map is the answer. It's like the range of platforms that we have has never been wider. And there's a issue of just install base. So I've drawn this graph by hand because I couldn't get accurate enough data, and I want to just indicate this graph is BS. But it's reasonably right in the broad strokes. So I didn't label them also. I want you to take a guess. On the y-axis is billions of people that own one of these devices, or really more accurately, the number of these devices that are owned by people, because burner phones are a thing. If you know someone that owns 4 phones, you should probably find new friends. On the x-axis is year. And so what is the thing on the bottom, the thing with the lowest install base? Your hint is their consoles, their PCs, and their phones. That's what's up here. I guess mobile devices, more accurately. So what's the bottom one? Consoles. And it's up to around 1 billion or so. How about the next one you can guess is PCs, 2 billion. And then phones is more than there are humans. And it's obviously the first one that's like saturating the market. So phones are a very, very important device and will probably remain so, because I doubt 500-watt phones will ever be practical. This has real implications for rendering budget. The PC and console, though, are still going up, so it may just be that people don't do 60 frames per second graphics on their phones 10 years from now. Who knows? It's really hard to predict these things. Another thing, when I first got to NVIDIA in 2008, the conventional wisdom was PC gaming was dead, consoles will be 100% of the market. Didn't happen, probably because of Steam, but who knows why. So, you know, predictions are hard. But if everybody has a phone, then everyone can have graphics, and then graphics are democratized. There's some implications of this that are a little uncomfortable for a hardcore rendering person, which is, you know, most of these devices will kind of suck from a graphics standpoint. So maybe we ought to back off on high levels of realism. But I want that, shadow to be perfectly anti-aliased and soft and beautiful. Well, maybe the good news is different devices can just have a different call for that shadow algorithm. So the way we decompose lighting may solve some of this. But there's a real image quality versus how many users you get trade-off here. This is just uncomfortable for me personally, because I've always wanted as much hardware as possible, because raise per second is what I want. So if we have this democratized graphics, and most of it is games, which I didn't say, but it's true, you don't want realism, you want like entertainment. And so this is a scene from the game we released in October. Like, this is really from just a rendered video game going out to the whole world. This isn't realistic exactly, it's much more cinematographic. Is that a word? It's much more supposed to be beautiful and engaging, like a film. And so things are exaggerated, like the tone mapping, some of the color grading. And yet, all of the assets in this game and every other game I'm aware of are totally physically based. Like, the artists measure the stuff, the albedos are right, the BRDF and microfacet distributions are right. Why is that? That seemed like a funny thing. And the roots of that are from predictive rendering, where, like the Omniverse project at NVIDIA, where they need to have the car not only look realistic, but really look like the real car that is eventually manufactured. Predictive rendering needs all of that physically based stuff. The renderer at Activision that produces Call of Duty looks almost exactly like one of those predictive renderers. And that just seems strange to me because it's so expensive and you want stuff to run on phones. So that's just a confusing thing I'll address a little bit in the future. Okay, that brings us to the present. Let me just comment that I think this is the most interesting time to have been in graphics of the time I've been in graphics. So many people think graphics research peaked in 1984. Like, you look at SIGGRAPH 84, it's just amazing what's in there. And then I joined in 85. So it's been all downhill for me. But I think right now is when it's most interesting. We have no idea what graphics algorithms are going to look like in 5 years. So what is the future going to be? And for the next 10 years or so, I think I know. That's the future. And let's look now at a bunch of stuff. I said that I was only going to look at the survivors and the saber-toothed tiger part of the talk. Now I'm going to look at the stuff that didn't make it, but seemed like a really good idea. And I think we should revisit all of them. One is point-based graphics. The Nerf stuff at some level is kind of point-based graphics. Gaussian splatting has a lot in common with it. Points are super attractive. Triangles keep getting smaller. That was the whole point of point-based graphics back in the day. Once triangles are sub-pixel, why do you have 3 vertices? You should just keep a point. And this was such a popular idea, there was actually 4 of these point-based rendering conferences, and then it died. Who went to one of those? I actually went to one. Yeah, I guess the people that went to it died too. Should we be in graphics doing just some kind of crude graphics that doesn't look that good, and then doing style transfers? Just have a big honking neural net that does not just denoise, but hallucinates. And this was a super cool paper out of Intel that just said, let's take Grand Theft Auto images and then train it with real driving video and make it real. So this is a very likely outcome, if we were betting, that graphics will get worse and worse and worse, and we'll use very crude graphics and then enhance it with a super denoiser that just hallucinates, say, the indirect lighting, whatever. This is a lot harder. Like, I actually expected, after I saw this Grand Theft Auto paper, I was like, oh, in a couple of years, this will just be the way we do things. It turned out to somehow be harder than was expected. Denoising has a lot of nice statistical properties and somehow is more tractable than hallucination. Hallucination is dangerous. Is Restir just going to take over the world? It has like a very fresh way of looking at things, and just every new paper, it's like, really? You can do that? So this is not an old idea that failed. This is an old idea that has not yet proven itself. But it's certainly very promising, and there's certainly a component of people, some in this room, that just think it's going to take over the world. Another thing that might take over the world is Nerfs. So I went to CVPR, the big computer vision conference, a month ago, and in the poster session, there were over 100 Nerf posters. So my reaction to it was to say, I'm going to skip to the next aisle. I think it's super cool, but I cannot keep up with the number of papers that's coming out. And this is just an amazingly elegant algorithm. There's a lot of progress on relighting it, which is really be the key for it to use in, say, a video game. And the thing I really like about it is its elegance and its compatibility with scanning, because it's really much easier to scan now. So what may win in the end is whatever is best for dealing with scanned data. How about voxels? We saw a nice paper for Antoine this morning. It brought a tear to my eye because I love this area. I feel like this ought to be triangles. I've always thought that. I've always been wrong so far. But I keep wondering if this is like neural nets, where just the right thing will make this take over, because LOD is just the nightmare of any graphics system. And this is a very elegant LOD solution. It's very compatible with scanned data. I love its like brute force hammer approach to things, which triangles have shown us is just kind of a good idea engineering-wise. So the trouble with a lot of these voxel-based techniques is going the last mile, voxel-based artifacts. It seems like neural nets ought to be able to just take care of that, doesn't it? There is an issue with animated content. So there's a whole content pipeline thing that I do wonder, again, if we're in a local minimum of we have this whole production workflow thing, it's very hard to shift to something else right now. Okay, what about stereo? Speaking of abandoned ideas, I just said the public rejected this entirely. Asus and a couple other companies have this amazing technology that just tracks your eyes now so you don't have to put on glasses. It's single viewer, which is unfortunate, but this is the first stereo monitor I've seen where I was just like, oh wow, that's really good. So if you haven't seen one of these, take a look at them. You can, if you have a hardware budget, just order one of these laptops. They're not that expensive, and it's impressive. Like I would love to play a tabletop game like Zoo Tycoon or something with this kind of technology. I got to say, I don't want to watch a movie on it. Okay, how about just render on the cloud? That takes away all this mobile, I only have 10 watts thing going. And it works. Like, I went and bought a GeForce Now membership, which just let me hop in the queue. You currently can only use games you bought. But I played Call of Duty on this system, and it was friggin' awesome. So as far as I'm concerned, cloud gaming has been solved technologically. So it's just a question of societally or economically does it work, which is not my department. But it has certain implications, I think. When I sell you a GPU and you play a ray trace game, you pay your power bill of 500 watts. When I'm running a cloud business, I pay that power bill. But I also have full control over the hardware. Imagine that if you only had one hardware platform that you had to target as a software person, wouldn't that be beautiful? Okay, maybe this 60 hertz thing, is a bad idea. Maybe we just get rid of all of this complicated denoising and do something really simple and just have the eye denoise with like super high frame rates. Joseph here in the audience somewhere. Joseph, where are you? He's somewhere here. You didn't skip my talk, man. Okay. He has a super cool demo of this. It's a very compelling brute force idea. And the screens are getting much better. So just a little thing I didn't talk about too much is screens kind of didn't progress very well until like 10 years ago, and then suddenly, bam, screens got so much better so fast, and that continues. Okay, now here's a crazy idea that first came to me from Chris Wyman, which is, can we just stop computing visibility? We've been doing that for 50 years. It's been a big pain in the neck for 50 years. What if we just didn't do it? Because we have an AI post-process coming anyway, it can sort that out. If I were going to start a PhD thesis in rendering tomorrow, this is what I would work on. Keep in mind, most PhD theses turn out to be bad ideas. You can take some risks there. But I kind of feel like this is a crazy idea whose time may have come. And visibility is a pain in the ass. You still need to cull. So that's part of visibility, and maybe culling is hard enough that just getting rid of visibility and what's in frustum wouldn't matter that much. But all of these ideas that I've just talked about for the future, they are really revisiting old graphics algorithms, and with a new twist. Usually there's a neural net in there. A key thing is historically graphics and graphics algorithms have co-evolved, and the trouble is you need to convince a multi-billion-dollar company to build this chip. So it's become very hard to do this work in academics, although Eric Brundtland, who's here, did do quite a bit of the ray tracing hardware work. So you can do it with simulation if you have the right hardware infrastructure. I feel like we should be doing that more again, is saying what would bake into hardware best? Because really, we have this general purpose GPU and this general purpose CPU. If Moore's law is over, maybe we should be doing special purpose something PUs that work for some rendering algorithm, and that's all it does. And that's certainly what these authors of that architecture book many of us had in school said in their Turing Award lecture is, now that Moore's law is over and we're getting better at fabricating and designing things, it's finally, we're going to have special purpose hardware for something other than graphics. But I think we should also have it for graphics, now that the GPUs do so much. So last thing in this talk is just a little observation of what rendering is. So what we have historically done is said, oh, let's do PBR rendering. Then it's too slow. And then we look at efficient rendering, and it's fast enough, but isn't realistic. And so one thing we could do is just use AI to project into there. But what's done more in practice is we do some stuff that looks real. So we make up some physics. We say, this is the physics we'll approximate. It's not complete. And we try to find something that's on the border. Now, there are a lot of other things out there that we're doing. And so you end up with all of this stuff. It's visually rich. It's this or that. And that gets back to, why do we do physically based rendering for all these things that don't need physically based rendering? And I think what you automatically get just as a sidecar on physically based rendering, you get consistent assets. That's why I think we use it for games like Call of Duty. You have 500 artists working together on gigantic models. If they all have to make real world assets, they will be a visually consistent set of assets. So good. You'll get visually rich lighting if you just use realistic lighting. You'll have, diffuse bounce looks good. You'll get good spatial cues so that you can tell where you're navigating in this virtual environment. And it's compelling. The real world's compelling. But do you really need all of that? Do you need physically based rendering to get that? No, there's probably ways to get this that are not fully physically based. And this is probably a good way for us to find efficiencies, but it will require a more subjective approach. Now, the one I've been thinking about quite a bit is visual cues. I think that's where ambient occlusion has been very helpful. You can really tell when something's touching. And this is some old work from Bill Thompson's group at Utah back in the day. And it's like anything works as a shadow, especially when it's dynamic. So that negative shadow there, that worked great as a spatial cue. That weird diffuse bounce that's orange, it worked great as a visual cue. So the question is, are there more efficient things that provide this visual richness and spatial cues that are less expensive? And the answer may be no. The only thing we know about so far where that is definitely true is ambient occlusion. So what are the 10 cousins of ambient occlusion we should have is my question. And maybe they're none. But it took us long enough to come up with ambient occlusion. I do wonder if there's some other things out there. Okay, so this is the most disturbing slide in here. Is the old way, like everything all of us have ever learned before 3 years ago, going to be modified so that we have an AI post-process and maybe an AI to help clutter or something like that? Or is it going to be entirely replaced? Now, I can run the clock out, but those of you who are younger should worry about this. And so here's what's possible. A possible future is no one in this room will ever again write an algorithm. You will only make up loss functions. Now, that's not actually that terrible a thing because we're often doing that anyway in how we tune our algorithms. But I'd start thinking hard now about what are the right loss functions for graphics? Because if you can come up with that, You can probably gain a lot of efficiency, and it can address some of the issues I had in the last slide. So what are the seeming constants of the last 50, 60 years of graphics? Okay, elegance of brute force wins. Brute force is good. I think this term was come up with first by Kurt Akeley. I heard it a lot around back in the day, all from NVIDIA people. Special purpose hardware good. And we're drifting away from it a little bit, so it'd be interesting to hit that again. Physically based assets good. Here's the most surprising one to me. C++ has got a 40-year total domination and running strong. That's what I code in today. It's unbelievable. I won't say whether that's good or bad. I just will say it's amazing. The frame rate has been remarkably constant. And where are we headed? So I'll let you read that. The one that really concerns me is where do we get loss functions from? Like, you go to any of these AI papers, it's like, what's the loss function? What's the training set? What's the architecture, the neural net architecture? The loss function for us graphics people, I think, is where the action really is. I don't think we're very good at thinking about this yet. So that might be my other thing I would do right now if I were just starting a PhD thesis. Final slide. I thought I should make, because basically I haven't really said anything about where I think things are going. I've said where I think things might go. So I have a bunch of predictions. I only make one, and I pick the one that I think will have the most negative reaction from the room. So here is my prediction. We can do all this real-time ray tracing on a desktop GPU. Cyberpunk looks freaking amazing. But I think baking will always be with us. So when this guy, whatever he takes out of that oven, I say that most of the software will still have light baked in it, because most of the people out there in the world are going to be running on 10-watt systems. So yes, ray tracing will also always be with us. And if you want to do predictive rendering, you will go buy a $5,000 computer and you will do this amazing stuff. If you want to deploy a game to 100 million people, I think you're going to use baking. I think there are other reasons baking will survive other than efficiency. I actually think baking, in many ways, is better. So I will leave with that. We can have that discussion at the reception tonight. But just say to yourself and say to all your friends that Pete says baking will always be with us. Thank you.
Thank you, Pete. Very inspiring, very nice talk. Thank you very much. So we have time for questions, comments.
And what did I get wrong? Is there anything factually wrong in there? I'll be shocked if the answer is no.
Thoughts? Yeah.
Frame interpolation has come back recently? Is that what you said? Mm-hmm. So could you repeat that question a little more? I got the frame interpolation part. So frame interpolation, actually, I have not read anything about since the 1980s. So in-betweening for film was like a thing. I think that Lavoie did some papers on like Hanna-Barbera cartoons back in the day, Flintstones and stuff, and it worked. But they had like 2 frames they were interpolating between, and the challenge of real-time graphics, of course, right, is you have an asymmetry. You don't have the next frame. But TAA is kind of doing frame extrapolation, right? So one question I would have too is, actually I'm just now confused straight up. So if Joseph wants to do 240 frames per second or 1,000, very noisy, and just not do any smarts, just have pretty crappy frames, but you do temporal integration with your eye. And then a more hardcore person wants to do 30 frames per second, and then really even do 15 and do really careful interpolation, because you have a lot of time then. These seem like very different philosophies, let alone the algorithmic thing. I'd say it's entirely empirical. Since I predicted TAA was a terrible idea, I don't want to speculate too much on this one, but I see your point, that smarts, real smarts in the interpolation could be good. Aaron.
I think training is the new baking.
Training is the new baking. Yeah, that totally could be. Bill Thompson that I had in here, he kind of was pursuing something like that, but not quite with AI. He was like, all this indirect lighting stuff, no one can tell if it's right, but it has certain patterns. You know, it gets lighter into the corners or darker into the corners. And so he was kind of used his own neural net to infer what the patterns of realism are. And I would say some of those final things I was kind of vaguely hinting at, which is maybe hardcore physically based rendering isn't what we need. We just need the right visual richness to have a compelling experience. That would seem to help training. Like training will get simpler if we get at better loss functions. So I'm not going to argue against you on that.
What about baking with Nerf or baking with a...
Baking with Nerf? Now, a baking, probably reviewers won't like anything with word baking in it. So I would combine Nerf with some other word, but... But if we can find a synonym with baking, I'm with you. Pre-computed global illumination via Nerf. But Nerfs actually, you know, there's a lot of patterning in them. I hadn't thought about it, but if you just went and took Nerfs of many scenes, there's a lot of information about what are the characteristics of rich lighting in scenes. That might be just a great training set, is measured Nerfs of real environments. Because it does just give you a light field in the room, right? Oh, this is a good idea.
Something else?
Yeah. Oh yeah. You read my hedgehog blog post. Okay. This I can't answer. So I think computer scientists make this mistake constantly, and I would say this is the repeated mistake I made throughout my career, is thinking your intuition is good. So you say, oh, this is a very elegant algorithm, so therefore that's what should win the day. Oh, I don't like this one because it seems inelegant. So quick sort bad, merge sort good. And you often are just wrong empirically. And so the blog post he's alluding to is the hedgehog just seems like the crappiest design for an animal ever, because you invest all your resources into these thick spines, very small brain, incredibly all-in-one, 100% all-in. You'd think evolutionarily this would make you very vulnerable to changing conditions, and yet it's like the super creature. It hasn't had to change this design in like 40 million years or something. And instead, you would think something like that saber-toothed tiger with its big brain and super teeth that can cut in anything would be awesome. And it turns out it was very vulnerable. I would say this is pretty similar to the algorithms we have, where it's like, why do triangle meshes survive? It's just amazing, really. Oh, point-based rendering, that's very elegant. It's just very unintuitive what wins. And so I think we just have to be super empiricists about what wins and not try to fight it too much. We also have to be aware, though, that ecosystems change. So we as a field over-abandoned neural nets, right? And then it's just our tendency as researchers to go all in on what's winning right now. So ironically, I think the computer vision field, which rejected every neural net paper it could get its hands on for 30 years, now will reject competing things to neural nets. I don't think they like internalize the lesson of their discipline, which is kind of the extreme case of some dead algorithm coming up from the ashes and just taking over the world. And we should be open-minded to that happening to us. And so I guess that was really where my baking will always be with us statement comes from, is I think that's something what we're thinking of is dead. I also, just seeing how the artists work, I've become a real just emotional fan of baking, so I'm also committing the crime I'm talking about of using my intuition.
Okay, I think we are running out of time. We have a banquet soon, so thank you very much. Let's. And
where is the banquet?
Johan has
tell
some
us
announcements.
where it is.
Okay. Thanks, Pete. Let me steal the podium here. Bear with me for just a second. I want to review some things in case you missed the opening session about the banquet here in another hour or so.
I didn't miss it, I just didn't listen.
Fair enough. All right, hopefully this picks up quickly. Right, so we're in the Chambers Grant Salon, which is physically in this building. It's at the basement level. And we're going to have dinner and drinks this evening. We're going to start at 6:30. The dinner will be served about 7:30, and then we'll wrap up by 11 p.m. Now, we actually have to vacate this space, and we have to do so fairly quickly. I understand the elevator's a bit of a bottleneck, so be patient, but they do need us out so they can turn the room over. And because of that, then we're going to use a different entrance, right? So if you see along 14th Street here, the studio loft where the awning is, where you enter each morning, just continue down 14th Street, that's away from the convention center, to, cut the name off. I don't know what that street is, but the next cross street, you'll turn left, and there will be a separate entrance for the Chambers Grant Salon. And again, that's where we're going to be. Keith has assured me there will be signs up directing you, along the path to get there. There will be a doorman there to let you in. And again, we'll be kicking off that at 6:30. So we hope to see you there. Again, our banquet sponsor, we have Reality Labs Research to thank for that. And we'll have a few words from them this evening during the banquet itself. So that's it. We'll see you in about an hour in the Chambers Grant Salon. Thanks.